Okay, it's 9:45. Let's get started. Good morning. So, what we are going to do today is I realized that yesterday's last task, the tutorial part, there are still some confusions. Some people were not able to solve it. So, I'm going to spend some time on that review. Then we'll take a look at the resilient modulus models today again, and then try to see what are the model parameters, what do they signify and stuff like that. And then we will go into permanent deformation, which is rutting and rutting models. We will again look at a rutting model determination and stuff. And then for the tutorial today, there are a couple of things. The rutting model rutting model fitting is very easy. We don't need to spend much time on that. But we will look at some DCP data and some lightweight deflectometer data and of how the subgrade characterization works and stuff. And if time permits, I may do a little bit of something like an illipave or something today, because the plan for tomorrow, based on the discussions for the first 3 days, I think one of the areas that you will gain more from is if we go into a little bit of what kind of instrumentation gets used to measure what in the field and how that data is useful as we make inferences about it. So tomorrow I am hoping to spend pretty much the entire day on talking about different projects with sensors and what the sensors give and how you can use the sensor data to make sense of different things. So we'll see. That's the plan. Again, it can evolve based on discussions. Sorry about my voice again. It's starting to get bad. Hopefully I survive tomorrow, and then I don't care. So let's start this. What I'm going to do today is so December 12, 2024. Okay, and is it visible clearly? Okay. So what we can do is, let's look at the MR models again. So the first one we are going to look at is the K theta model, right? And so the formulation is K theta raised to the power n, where theta is the bulk stress, and that is sigma 1 plus sigma 2 plus sigma 3, and that is bulk stress. And K and N are model parameters. And for dimensional consistency, we write MR is equal to K theta over P0 raised to the power n, where P0 is equal to 1 kPa or 1 psi, anything. It's basically unit pressure. You are just trying to make it dimensionally consistent, right? So what we are trying to do, there was one question that I had yesterday, is in our laboratory test data that I shared with you. The question I had is, where do the models come into picture in that test data, right? The answer is nowhere. The models have nothing to do with your test results. Testing is just to determine properties of the materials. Model running so that you can mathematically represent that test. There is no obligation for you to fit a model to a test. Is that clear? You don't have to fit a model at all. So where do K, N, K1, K2, K3 come into in the test file? Nowhere, right? So that's something you have to be very clear about. Model, you are only, it is quite possible that you can spend your entire life only running tests and not fitting a single model, if that's what your objective is, right? So your test data will not give you any of these parameters. The parameters are needed because you are going to do some calculation for which you want to represent MR as a function of stress state. That's basically the whole purpose, right? So how do you do this? So let's just say somebody pull up on your laptop the columns you have on the test data. Any with a laptop, but just open, because I don't remember. So if you go to that test data, we had, I think the first one was sequence. Second, I think, is called pulse group. Then we had axial base stress. Then we have axial deviator stress. Then I think we have radial base. Then we have radial deviator. Then I think axial resilient deformation 1, axial resilient deformation 2, and several others, which honestly we don't use in this exercise at all. Let's people who had difficulty, please fitting that, please make sure you take notes and stuff, because I don't want you to leave this class not knowing how to fit a model, because this is probably one of the most important ones. The sequence here starts from 0, and if you see, there is a 15 as well, but that 15, if you look at the stress states, is actually pretty value. It's basically a test ending protocol, so it's not an official stress sequence. So you only care about 0 to 14, which is the 15 stress states, right? So this 15 in your file you can ignore. You don't have to do anything, okay? Because resilient modulus test, we said there are 15 stress sequences, right? So 0 to 14 is 15 stress sequence. Then pulse group, for everything we had 1, 2, 3, 4 pulse groups, okay? What I said is the a resilient modulus test, for every stress sequence you have 100 pulses per sequence. Because this is a research equipment, what it does is 1 to 25 it merges into pulse group 1, 26 to 50 is 2, 51 to 75 3, 76 to 100 is 4. What did I say ASTO T307 does? It takes the last 6 cycles and then takes an average. In this machine, you don't get last 5, you get last 25. So you just have to use that. That's basically what it is. Okay. So what I'm trying to say is you are doing this 76 to 100. So this is the pulse group of interest for you, right? Okay. So now you have 15 stress sequences. So in your Excel file, you delete 1, 2, 3 stress sequence for all the 1, 2, 3 pulse groups for all the stress sequences. So in the end, what do you end up with is 0, 1 all the way to 14. So this is your sequence, and then this is your pulse group. You will have 4, 4, 4 all the way to 4. Does that make sense? Okay, those who got it yesterday or were able to do it, you saying yes does not mean anything to me. I want yes from the others who were not, because I don't want this to end this class without that. So 4 is all we are doing, right? Now let's go step by step. So this is the University of Illinois fast cell, and what I said is there is independent control over the vertical and horizontal. So what you have here is sigma V0, sigma Vd, sigma H0, sigma Hd. That is how you are controlling the stress state here, right? You are independently applying the confinings, independently applying the deviators. So what does that mean? So this in your data sheet, this is axial base stress. This is axial deviator stress. This is radial base stress, and this is radial deviator stress. Make sense? That is what your stress sequence or stress meanings are, nomenclature. So sigma V is equal to sigma V0 plus sigma Vd, right? And sigma H is equal to sigma H0. It would have been plus sigma Hd if we were pulsing in the horizontal direction as well, right? In this case we are not. So what I am going to do is I am going to write sigma Hd, but I am going to circle this and I am going to say this is 0 because vertical pulsing only. That makes sense? Why do you have little values in there? That's because it's just sensor. It's sometimes sensors carry garbage and stuff. You just have to ignore that. So now you have, and because it's a triaxial test, we can replace the V and H with 1 and 3, right? Major principle, minor principle. So sigma 1 in this case is equal to sigma V0 plus sigma Vd is equal to sigma V, and sigma 3 is sigma H0, right? So now what you have is, that's the stress. Let's take a look at the definition of MR. What is MR? MR is sigma d over epsilon r, or recoverable strain, not deformation, strain. In your data file you are given axial resilient deformation 1 and axial resilient deformation 2. You are given those because there are 2 LVDTs. If you compare the data, and this is what you should do when you are running a test as a researcher or something, when you compare the data you will see they are not identical. That basically means the system is not really always moving exactly vertically. Again, that is granular material test, that is how it is. If it's exactly identical, you can actually question the data. There's something weird happening. So aggregates don't behave like plastic or something, right? So what you are going to do is take average and to determine average axial deformation. Then epsilon r is nothing but delta average r divided by specimen height. Which is 150 millimeter in this case. Yes. So now what do you have? If your table, if you now want to take draw your table again, I know I am doing this repetitively because I just want to get it in your brains. So sequence number, pulse group, now we can eliminate because it's only 4, right? Every pulse group is the same, there is no difference in that. So I'm going to eliminate that column. I'm now going to say sigma V0, sigma Vd, sigma V, sigma H0, and then now I have epsilon r average, right? We just calculated all of that. So if you do, let's just say sequence number 0, and I'm going to just write it in PSI just so that my hand calculations make sense. So your sigma B0 should be 3, this should be 3, this is becomes 6, this should also be 3, and then epsilon r is something xxx. So then your MR becomes sigma vertical deviator divided by epsilon r. So sigma vertical deviator divided by epsilon r. Yes, this is your first check. These numbers should match what the software is already giving you, and we did it and it matched, right? So now you have your data. So is the data reduction part clear? Yes. Now we go into, so this is test results. Again, I want to highlight, your test results have no implication to your model. If you want to fit the model, that's different because you want to do something else. Your test is your test. So now the question is, now you are trying to go and fit models. What are you going to do? Let's just do the k theta model first. So I said MR is equal to k theta over p naught raised to the power n. We are now going to fit this model. There are many ways you can do this. You can actually plot MR against theta and exponential, not a power curve on Excel. It will directly give you this. It does. You can try it. It's very simple. But the point is that does not teach you how to do it manually. So what we already always do is log MR is equal to log K plus n log theta over P naught. So, and we said this is of the form Y is equal to, this is C, this is M, and this is X. So this is of the form Y is equal to mx plus c. So if you now just take a random graph, plot log theta over p naught, which is basically theta, I just write theta over p naught to be consistent, and you plot log mr, you will get a line like this. This intercept is what? log k, and this slope is n. So you directly get your n. You don't get k directly. You have to take your intercept. So intercept is equal to log k. So that means k is equal to 10 raised to the power intercept, because I am doing base 10 log, I am doing normal log, and n you get directly. So then you can write your model as mr is equal to k theta over p naught raised to the power n, and you just obtain the two numbers. That makes sense what we just did? It's just a matter of plotting the graph, and then you can check. Pushpak, did you realize where you made a mistake or something? Because you said you're getting some weird values. Maybe we can take. No, we don't need to. As long as all your units are the same, it doesn't matter. I wrote PSI because that's the numbers I remember. If you delete it and make it KPA, I don't care. I mean, if that makes you happy, I can actually change this. I'll just make it KPA, and I think I'll just. I don't remember it. Does anybody remember values from anybody who finished the model? Okay. That's what you got. Okay. I don't remember, honestly. I honestly don't remember. I can run it on my MATLAB code and take a quick look. Uh, yeah, 0.56529354.55, right? So that's what you should be. So if you're not, then check your numbers. Maybe you didn't eliminate the last stress state or something like that. That's probably what happened. The 15 needs to be eliminated. But anyway, is the procedure clear for everybody, what we're trying to do? Now, the next model is the USAN. If you want to go into USAN, the formulation becomes MR is equal to K1 theta over P0 raised to the power K2 sigma D raised to the power K3. Now it becomes a little bit complicated to directly fit a power curve or something, because it's a multivariate problem now. But the good news is you can do multiple linear regression in Excel very easily. You can still do log MR is equal to log K1 plus K2 log theta over P naught plus K3 log sigma D. Actually, it should be P naught as well. And then you do what is known as multiple linear regression. By the way, one thing I give you some idea. Education in your time right now and research, I mean research my time as well, because I'm still a researcher, right? I'm not in school, but I learn every day, has become extremely easy with the tools like ChatGPT and stuff like that. Make good use of it. You know, people think it can only be used for plagiarism. The answer is no. It can actually be used to educate yourself a lot, right? I learn, I would say, 75% of my coding from ChatGPT. If I'm trying to do something, I would just say, okay, give me a code to do this, and then I take it and then I modify it and then I do the things. There is no point in reinventing the wheel and stuff like that. So if you don't know how to do multiple linear regression, yes, these are things you can even find YouTube videos, but just type in ChatGPT, it will teach you how to run this thing, how to model fit in Python. It will actually teach you do that. That's basically how you build skills, folks. Not for everything, at least especially researchers. If you rely on courses to learn everything, then you'll be taking your entire life. You'll hesitation. You have to teach yourself things, right? And that basically, like when it was COVID time, I actually, because the schedules were wrong, that's actually the period I actually sat down and taught myself how to code R and how to code in Python. I had never touched my entire life. I've been a MATLAB coder. I didn't know what Python was, and I was a SAS coder for statistics. I do SAS programming, but then I taught myself the whole thing. I just watch YouTube videos. NPTEL, I'm sure everybody knows what NPTEL is. In my research group, when students join, the first thing I do is I pull up NPTEL web. I said, this is what India is doing. Go. You guys are not using it is very embarrassing. If you are not, you should, right? Make good use of it. I mean, there is actually a professor in IIT Kanpur. He does a lot of statistics teaching. I actually took, like, during COVID, like 4 of his classes, and that's how I taught myself the entire R coding and everything. If you want to learn, there are pavement design classes. There is everything is there. Everything is there. So just make sure you do that. Scroll up. Which way? This? That's it. So if you don't know what to do with the code and stuff, just use ChatGPT. In fact, you can, I don't know how much you all have played. How many of you have played with ChatGPT extensively? It can do everything. I have copy pasted blocks of code and asked, what does this code do? And it explains what it does. That's how you interpret code as well. So if you take my MATLAB code and you have no idea, just copy paste it and say, what does it do? Tell me. And it will tell you that this is what it's doing. It's very, very useful, folks. Just make good use of it. Self-learning is the best learning. I mean, people can only give you directions. The very last one is MEPDG, or the universal model. That's MR is equal to K1 PA theta over PA raised to the power K2 tau octahedral over PA plus 1 raised to the power K3. Exact same thing. Linearize, fit the multiple regression. You just have to keep track of what your intercepts are. You can't do blindly. You can't jump. So if you log MR, log K1, well, it's probably easier to do this. I think because MR is a value and PA is 101.7 or whatever you want to take, like depending on KPA or PSI, I would say just divide the PA directly over MR because it's a value. It's going to make your life much easier. So log MR over PA is equal to log K1 plus K2 log theta over PA plus K3 log tau octahedral over PA plus 1. Just have to plot, just have to determine this is the y variable, this is x1, this is x2. x2 is not a ratio anymore, it has a plus 1 in it as well. Just make sure you add it and you fit the model. Then you get your slopes. Again, intercept is log K1, not K1 directly. Slope number 1 is K2, slope number 2 is K3. That's pretty much it. Does that help? Do you think you can finish this now? Yes? If you just follow this, it should be straightforward. Because we are on the topic, let's visit a little bit one thing here. Let's take a look at we said granular materials are stress hardening and and the most common way of modeling them in the past was for granular materials. It is usually the K theta model, right? It's the bulk stress model, or it's a helping. It helps it captures the hardening really nicely. And for subgrade soils or fine grained, it was actually the bilinear model. What is the bilinear model? It basically is this. So you plot it against sigma d. This is MR. You have a first linear component, second linear component, and you can K1, K2, K3, K4. There are 4 values, and you can just do. But the point is, when you are trying to do any modeling, right? What are you going to use? You don't have. What if there is a mixture of materials? What if it's an aggregate and a soil mixed? How do you isolate them separately, right? That is the reason they came up with the universal model, right? The one model, MEPDG. MEPDG is not for aggregates only. MEPDG is not for soils only. MEPDG is unbound materials, complete. Okay? So what it does, and it's basically the USAN model, like a modified USAN model. But if you look at it, MR, K1, PA, theta over PA, K2, tau octahedral over PA plus 1, K3. And what did I say tau octahedral was for a cylindrical triaxial? Anybody remembers? Square root over 2 over 3 sigma d. So it's basically a constant times sigma d, right? So that's why I say it's a modified USAN method, because it's basically like a sigma d plus 1 kind of a formulation. Constants will just play certain roles in there. Your coefficients are different. For aggregate materials, stress portion that actually represents the stress hardening properties. For subgrade soils, it is the K3 portion that actually represents the stress softening. So what can you say about the sign SIGN, not SINE, sign SIGN of K2 and K3? K3 will be negative because it has to pull the value down, right? So your K3 values are always negative because it is the stress softening behavior that it models. Okay? Whereas K2 is the hardening behavior. K1 is an overall property, basically. It's always a big value. It's dependent on stresses and stuff like that, properties and stuff. So now the question becomes, so I wanted to address this because at least for the master's students and stuff, I don't want to leave a gap by saying that, okay, model, right? Why these models? The objective is that we are trying to capture the stress dependence of these materials, and we are trying to predict what the modulus is going to be if we know the stress states. Okay, now you will see that even in MEPDG, like the mechanistic empirical pavement design guide, the forward analysis, or the, for how I said it's not really a design, it's basically analysis and performance prediction. So the analysis part is done by what is known as a multi-layer elastic formulation or layered elastic theory, which is what your IIT PAVE is, which is what Min layer is, Wesley is, there's many, Chevron is, all of them. It's the same thing, similar concepts. So even in MEPDG, it's actually a layered elastic formulation called Win-Julia. Okay, Win stands for Windows, Julia stands for Jacob Uzan layered elastic analysis. Jacob Uzan, Israel, the scientist I told you, it's his writing. He developed the program. It's called Win-Julia, or sometimes people write it Julia because in Israel it's not Jacob, it's Yaqub, right? Yaqub, so it's Y. So Win-Julia is the underlying code for MEPDG. So what is it? It is a layered elastic program. What is the property of a layered elastic, or what is the main characteristic of a layered elastic program? It has multiple layers, and it is an elastic analysis, and the E value is constant per layer, right? What does that mean? Every layer has, the base has one modulus, the asphalt has one modulus, the subgrade has one modulus. So the question is, I spent all this time to teach you all this stress dependency and everything, and now I am telling you that we are not using. That's actually true, because when you, to represent a truly stress dependent material behavior in a pavement analysis, you have to go into finite element analysis. Otherwise, you cannot assign varying properties within a layer. FEM is very easy. It's every node has a different properties and stuff, right? You can assign that. But if you run a pavement over 20 years with traffic, with climate under FEM, take you 5 hours to run, 6 hours to run, right? That is the reason MEPDG, the trial version of the software came. There was actually a version that came with the finite element part built into it, and it was just prohibitively long to run. So that is the reason they eliminated it. Now it's a layered elastic program. So we are actually not capturing what is known as level 1 inputs for subgrade soils and aggregates in MEPDG. It's still level 2 and stuff, because we are not doing true stress dependency in there, at least as of now. There is plans to make that improvement, but it's not there yet, right? So now the question becomes, what should you do? Let's just say that you are now a researcher. This is a question for all the students doing research and stuff. Now I'm doing layered elastic theory or layered elastic analysis, and I am giving you some kind of a layered elastic program. I'm going to only draw the aggregate. Asphalt is on top, and I'm saying you are going to use only one E, but you have a lot of test results already to do this, to support that. Oh, I have the ability to capture stress dependence. I have the model, I have everything, but I don't have the analysis software to do this. How would you, what is your poor man's approach to somehow represent stress dependency in this? Who can tell me? Do you understand the question? So you have the software is able to take only one modulus per layer, but you know that modulus change within this layer. It should, right? But your software is not capable of doing that. What's your poor man's way? How can you cheat the system? You can sublayer, right? You can sublayer because your layered elastic system says and now you can do E1 1, E1 2, E1 3, E1 4 and stuff like that, and then you can change the modulus in there. Near the surface the aggregate is going to be stronger, assign a higher modulus there. Below that it can be lower. Slowly do that, right? Then the question comes is, can you do, yesterday I told you something called anisotropy as well, right? Standard finite element codes cannot capture that. Standard ones, they cannot. There are special finite element codes. One was actually developed by my PhD advisor. It's called GT PAVE or Geotech PAVE. It's not any more public here. But there you had the ability to model anisotropic layer behavior as well. IIT or anything else, you constantly come across. I think, if I'm not wrong, there is one out of, I think Minlayer is layered elastic. There is another one that actually does MICH-PAVE. MICH-PAVE is a finite element thing. It's a code. But again, you can only do so much and stuff. Okay. Before we move on from resilient modulus, there is another thing that one of you asked me. You asked me, I think, yes. Is about, he said NCHRP says to 7th sequence or something like that is what he said. So let's address that. What he meant is, I ran an MR for a soil, MR for an aggregate or something. I have sequence 1 all the way to 15, and I have MR 1 all the way to 15. So I have 15 different MR values from a single test for this material. And now somebody comes and says, hey, what is the resilient modulus of this material? The true answer is yes, it depends. It depends on the stress. If somebody says, still give me one number, I want you to give me one number. Okay. For that, there is something called representative modulus, and people have come up with an idea. HRPs, I think another document, they say that you take the 6th stress sequence out of the 15, and then take that value and report that one. Okay. Why they came up with, there are different theories. I will tell you something which is a much more robust way of doing this. Okay, and you will see how you can do that. Let us assume that you have access to a software like IIT. Okay, so it is stress dependent modulus. Okay, either today or tomorrow I'll show you the software, how it works and everything. We'll look at it. It can address stress dependent modulus. Okay. Now let's think of a way you can come up with one modulus value, and we have discussed everything for you to have this, and you may have to write this down with me so that you follow what it is going. Let's say we take a representative pavement, right? We take a pavement. So let's say it is something like this. So HMA, ag base, and subgrade is say 4 inches, 4 inches, 12 inches, and this is infinite. Okay, and let us say that you tested this material in your lab already, like this file that you work. That's, let's just say that is your material. Okay, so you now know the k theta values and stuff, k and n values. You know this because you have already tested it in the lab. Okay, what you can do is the following. You take this model, the parameters, like model parameters and everything, and then you put it into a software like IIT. And you know what you do? You predict or calculate, let's not do predict, let's say compute surface deflection as D0, D8, D12, D24, D36, all the way, like D60 or whatever, just like FWD. We have talked about FWD, so you know that, right? So you can do this. And what properties are being used to predict this? Actual stress dependent properties, because IIT is 100% capable of capturing stress dependency, right? So you do that. Then you know what you do? You take this surface deflection and then plug them into a back calculation code, just like the one we did here, right? And then you can calculate E1, E2, E3 and everything. Do you see what I just did? I took a stress dependent modulus model, I predicted surface deflections, and I fed it into an FWD algorithm or back calculation algorithm, and now I ended up with one modulus, E2. So that E2 is representative of the entire stress dependent behavior of the entire layer, because that is what you fed into it, right? So this is kind of a cheating or a way around, not cheating, this is kind of a smarter way. Take a complete stress dependent data set and resolve it into one modulus, because the response of a layer with this one modulus is equivalent to the response of the layer which was stress dependent property, because that is how you matched the surface deflection, right? So this phenomenon is called representative modulus. This E2 now becomes the representative modulus. And if somebody, some PhD student or some postdoc is looking for a research topic or something, I would say develop a code to couple the entire thing. Because linear elastic analysis back calculation is, you saw it, it's an Python code, it's an open-ended. You can write a FEM code. Again, there is enough documentation for you to figure it out how to do that. You can write an FEM code and you just say that this is my test result. Apply a 9 kip load or a half of an E cell onto the surface. Calculate the D0s and everything, feed in or feed into the FEM, calculate the D0s, automatically feed into the back calculation, automatically do like a scalar and stuff like that, and now find out E1, E2, E3. That's a pretty cool tool for you to go to the morgue or somebody and say that, look, now if somebody test data of resilient model can give you a single modulus, which is very representative of that length. Do you understand? There is no garbage of assumptions. There is no 1500 CBR. It is purely mechanistic. You're basically doing a mechanical. I think with somebody get research for money to pay them. So unless an agency actually wants to do it, I don't want a student to do this. Otherwise, it's very doable. Is this clear what we did? What is the concept of representative modulus? I think we should move on from modulus now. We have spent some time, quite enough time. Yes, K and N, you can do GIAN modulus. I don't think you can. I think you can do MEPDG. I don't remember. We can take a look. You have Busan model and stuff, so you can do. Sounds good. Okay, let's move on. Okay. So revisit MR models. We did that. Significance of the middle model parameters. We did that. Separate model versus universal model. We did that already, right? I told you this, why they merged this and stuff. There are a couple of papers I really want you to read. Okay. One of them, and both of them were shared with you yesterday. I just want to highlight those to you. There is a state of the art paper. Again, it's not state of the art anymore because it is a 2001 paper. But it's a very well written paper by Lecarp et al. On resilient modulus of unbound aggregates. Okay, and it gives a lot of details about how the models work, how the moving wheel load should be captured, what is the difference between constant confining versus variable confining, what are the effects of moisture content, what are the effect of aggregate type, what is the effect of low stress history, load duration, computational modeling, how it is done, how the different models are developed, where are the parameters coming from. There's a lot more models that we thought about and whatnot. So it's a very good read, and anybody claiming to be doing unbound aggregate research should not go without reading this paper multiple times. It's a very good, excellent paper on this. And when we are on the topic, although you don't know anything about deformation yet, I'll show you on the same year they published another paper called State of the Art 2, which is called Permanent Strain Response. And I've shared this with you as well. So it's one is resilient modulus, one is permanent deformation. Excellent papers. You should definitely read them if you want to have a good background of these concepts. Okay, let's keep going. Oh yeah, another one. Oh crap, I forgot. Another one. Again, I think this was sent to you as well last night when I was sending emails at ungodly hours. This is a literature review report that Errol Tutumler wrote when he was a postdoc. I heard he was just starting and stuff. It's called Granular Material and Soil Moduli Review of Literature. Again, it goes into all the models of resilient modulus and it discusses the details of them. What are the significant parameters? How were they developed? What are the advantages? What are the disadvantages and stuff like that? So again, if you want to write a literature review on this kind of thing, this is giving you 80%, 70% of the information. Excellent reference. I shared this with you as well. So again, read this again. I hope so, because we are now coming down to the winding part of this workshop, right? You know, half more day left today and then less you tomorrow. There's going to be some more philosophy than just technical talk, right? Don't do research without reading literature, right? Don't ever do that. At least every research, at least in my group, I encourage that every single work day of yours should have at least 4 to 5 hours of pure reading. No testing, no data analysis, reading, right? The more you read, the more ideas you'll get, the better your knowledge is going to be, the better prepared you will feel something. Otherwise, essentially what's going to happen is you come up with a brilliant idea, go to your advisor, and the advisor is like, yeah, they did it back in 2015. You just haven't read enough, right? So reading is very, very important. So please make sure you get enough reading done if you are into research line and stuff. Okay, let's now go into part 2 of resilient behavior or repeated loading behavior, which is permanent deformation. We talked about resilient modulus. Resilient modulus is an important input for your MEPDG, mechanistic empirical design and stuff. Repeated loading behavior, it's more of performance, right? It's not an input. We don't need a model input to run this or anything. But it is a very, very important component because it actually governs your rutting behavior and stuff, right? And rutting is a major distress that you have to address and whatnot. So it is an indicator of how much loading or what level of stress the material can exert, and then how does that affect the fabric of it. It's not really fatigue, but you can actually think of it similar to fatigue, because even if you are not near failure stresses or something, but if you just have many load applications, at one point the fabric of the aggregate matrix or the unbound matrix actually can collapse, and you can actually have, look at this curve, you have load repetitions on the x-axis, permanent deformation, and actually stayed. After some time it just collapsed. There are many factors that affect it. One is, where do you stand with respect to the failure stress of the material, shear strength, right? The way I explain it is, let's just say you are into weightlifting, okay, and your capacity is, I don't know, 100 kgs, right? To lift, you can probably do 50 repetitions, like not near my capacity or anything at all. But if you are lifting 8 kgs, then even after say 20 repetitions, you'll probably get very tired, right? So the nearer to the failure stress you are, the lower the number of repetitions before you actually start collapsing and stuff. That's basically what it can be translated into shakedown theory. I know some of you are studying shakedown theory and stuff. We'll talk about that a little bit. But how do you represent a model? We'll take a look at that, and how do you study it. So as I said, general resilient modulus testing. Okay, I think let's just get there. There is no standardized permanent deformation testing protocol. Okay, there is no ASTO T309 or something that is resilient permanent deformation. There is no. There have been proposed methods, there are suggested methods, but it's not standardized. There are many reasons for it. But in the resilient modulus testing, I said the sequence 0, not in the data. In the data, sequence 0 meant something else, but I'm talking about when you define the test procedure. I said it's a 15 sequence test, but before you start it, you do what is known as the condition, right? and the conditioning represents the material, initial breakdown or initial stabilization of the material. You can use that data as an indicator of the permanent deformation trend of the material. Okay, how many cycles do you run that for? I said 500 to 10,000 or something like that, right? Usually it's about 1,000. Like all the tests I have run, it was all 1,000 cycles, so it's about 16 minutes. 16 minutes is what, 960 seconds. So 40 more, 16 minutes, 40 seconds basically. So the point is, that's what this plot is saying. The general MR test procedure, if n equal to 1,000 or up to 10,000, or at least 10 or at least 3 log cycles. You know what a log cycle is, right? A 0 to 1, 1 to 10, 10 to 100, 100 to 1,000. That's a log cycle. So 1 to 10 is one cycle, 10 to 100 another cycle, 1,000 is another cycle. So at least 3 log cycles, if you run it, you will get some idea about the permanent deformation trends. Now, permanent deformation is not a very easy thing to capture immediately, because it is dependent on several things. If your material property, because it's a long-term phenomenon, right? If your material property changes, what does that mean? It's raining and your layers are completely flooded. Your material is not the exact same material as it was. So now your shear strength, so you're now lifting still 50 kgs, but you're lifting 50 kgs after partying for all night and not getting enough sleep or not getting water or anything. So your capacity has gone down. So it's not a factor of 2. It's not that your 100 kg is your capacity has probably gone down to 75. So the same load, if your material property has changed, is going to collapse your system now, right? Other way around is if the loading magnitude, right, whatever is designed for, somehow the loads are getting heavier, right? We actually run into this problem, if I am not wrong, in a lot of rural roads in India as well and stuff like that. Probably they didn't think about it. They just thought maybe a bus or something will go, and all of a sudden a tractor with a lot of bricks and stuff, like completely fully tractor runs on it and the pavement just falls apart, right? That's what is your design vehicle and stuff like that. So this is, you can actually get an idea. Construction and initial shakedown is where you have this exponential raise, and then it kind of stabilizes. A permanent deformation behavior should always be like this. It should always stabilize. Because remember what's happening here. Who can tell me? When we are loading here, what's happening? This is the hysteretic part, right? We talked about in the resilient modulus. That's the flat portion. So ideally you should be operating here. But that always stay flat? No, it can change because of many factors. The very standard model that gets fitted into permanent deformation, the most commonly used model, or to talk about, is what is known as a phenomenological model. Okay, is of the formulation AN to the power B. A and B are constants. N is number of load repetitions. Okay, at first glance, what is missing from this model? Well, we'll get to that. Modulus is an elastic parameter, right? We don't need that here. Let's just say material is constant, let's just say climate is constant. Yes, they are all true. I mean, you're all right. But for a given material, even you cannot anyway consider climatic or material properties. But what is missing here is stress. You're not saying what is the stress level under which this test is being run or anything. It's just an a n to the power. N is just number of load. How many people are there? Like, it doesn't matter. It doesn't really say anything. Go into the details of this model. Why it has worked over the years is because this a parameter actually is a function of stress state. You are not capturing directly the stress in the equation, but A actually captures indirectly the stress effects and stuff. And B is less sensitive to sigma, and it varies with soil type. So A factor, or different things like soil type, moisture, density, strength, and stress level. This is something we are going to hit pretty hard, most likely after the tea break today. Is the concept of what is. There are two ways to talk about it. First, sometimes people call it a subgrade stress ratio. Stress ratio as well, SSR. It's the same SSR. It can have two different meanings. We'll talk about this extensively after the tea break. The whole idea here is sigma d over QU. What is QU? Unconfined compressive strength, right? And then sigma d is deviator. How much are you demanding of the material with respect to ultimate value, the unconfined strength? That's called something called subgrade stress ratio. It actually affects your resilient modulus, permanent deformation significantly. We'll take a look at that. And in this, again, remember folks, why I said model fitting is very easy. Look, log epsilon p is a plus b log n. Does that look familiar? We just did it, right? Kn, k theta to the power n, right? We did the exact same thing. Oh, yeah, why did they do log a? It's probably log a, because a is a constant. They actually say log a is another constant, basically. You're right. It's not exact, but it's basically a is a. It's a constant. So it should have been ideally a prime or something, right? Log a is a prime. Some kuch alag naam. Yes, you are right. Absolutely right. But the whole idea, we have done this, right? K theta to the power n. So if I give you epsilon p data, and if I give you n, you should be able to fit this model very quickly. We just did this, right? A factors for granular materials, it's shear strength and the ratio of sigma 1 over sigma 3. Again, there is nothing called QU, remember, for granular. It. Now you're talking about holding it, how much we are torturing it, sigma 3. That's ratio. So this is what's affecting your permanent deformation. Permanent deformation testing is much less advanced than resilient behavior. It's not standardized. You don't have a standard protocol, but you have to, if you are studying the rutting behavior of a material, different people have different test protocols, different stress states. How are you going to test it and stuff? There's a lot of decisions that makes into subgrade and unbound batch material performances solely judged by their field performance deformation or rutting potential. So it's basically saying that I will make health condition by measuring or by looking at how your blood sugar is or something, but I don't give anybody a method to monitor their blood sugar or something, right? So that's essentially what you're talking about. So we don't have a standardized test method, but every time we do pavement performance prediction, we track rutting and we say, oh, it's bad. But we need to test it then. Not fair. How do you test it? Again, no standardization. It's repeated loading, that much we know. It is still Haber-Sign, that much we know. We have rest period and stuff, that's much we know. But number of load cycles can go from 1,000 to 8 million is what people have seen. So 8 million is 8,000, right? So can somebody do 8,000 divided by how many seconds in a day? 86,400 or something, right? Is it 86,400 or 84,600? 86,400. Can you do that? 8 million divided by 86,400. I just want to see how many days a test takes. 92. So it takes 3 months, right? Now imagine your advisor asks you to run 50 of these tests, then you are like lifelong PhD student or something, right? You never graduate. So it's very difficult to track, these long tests and stuff. How do you do loading? It's more common is CCP. There is actually a VCP procedure in Europe available as well. As I said, for stress states, for cohesive soils, you decide on something called subgrade stress ratio, SSR. Okay, and there are some rules of thumb, and I may not have a slide on this, but I'll tell you this. If you are, let's just say, you are helping an undergraduate student do a little design for a project or something, and they're like, hey, I'm going to put 5 inches of an asphalt, 12 inches of an aggregate and stuff. Is my subgrade going to be okay? You're going to say, okay, what do you have? Like, I don't have anything. I have only CBR. Like, okay, that's a good starting point. We don't have anything, and we still have to have a result. Let's do a CBR to unconfined compressive strength correlation. That's still okay because both are strength related, so you're still doing okay. So you determine QU, and then you run a simple IIT PAVE or something to determine the deviator stress on top of the subgrade. And then you take the ratio. The rule of thumb is that as long as it is less than 0.6, be fine. It's a rule. Don't ask me where. It's very empirical in nature. Of course, 1 means what? Say it again. Both are same. What does that mean? What will happen to your subgrade? It's going to fail, right? You're going to collapse. So sigma d over u, the rule of thumb, they say in very elementary design, is limited to below 0.6, 0.7. You should be fine. You will not have rutting problems and stuff. So you can, and coarse aggregates, you can have sigma d over sigma 3 or sigma 1 over sigma 3, however you want to do, and then you can monitor the delta P and stuff. What are the primary factors that affect permanent deformation? You can have applied stress states, you can have QU or tau max. Again, we're going to look at tau concept very in details after the lunch break, after the tea break. And then you take that. And the secondary factors, you can have moisture content, plasticity index, clay content, dry density, freeze-thaw effects. Okay. Now freeze-thaw is something, I don't know, maybe in northern India it's considered like really north, maybe, I'm assuming, but other parts, no, you don't really freeze. But freeze-thaw is a major problem, because freezing is a very good thing, right? Because ice is very strong, your soil becomes really strong. The problem happens when it's thawed. Now it becomes like a mush, right? And also, just you can do this test. If you take like a little soil cylinder and you put it in your freezer, and then you take it out, put it outside, put it in the freezer, take it outside, you'll see that the soil fabric actually disintegrates even if you don't do anything about it. The pore volumes and the pore structure and everything collapses and stuff. So freeze-thaw is a very big thing. So let's take a look at some of these. This block or this section is very data based. You'll see I have a lot of test results to showcase some of these things. So you have seen this. This is basically increased sigma increases epsilon b. These are two different materials: medium subgrade, soft subgrade. Medium subgrade, unconfined compressive strength of 23, and soft is 13. Two different subgrades. Okay. Sigma D, B and A, and look, the B's as the sigma D, so it's basically 0.14 to 0.17 for different stress states. So the B is not very sensitive to stress in the model AN to the power B. Okay. The A on the other hand can be very, very sensitive depending on the material and the stress combination. For the good material, relatively good, initially it was just some sensitive and then it became very sensitive at the higher stress states. For the soft material, throughout it became very, very sensitive, right? So let me show you what does that represent. So if you look at AN to the power B, right? Epsilon P is equal to A n to the power B. If you take log A plus B log n, what is log 1? 0. So A basically represents the put n equal to 1. 1 raised to the power B is, so epsilon P is, so A is this initial hammering that the material takes, right? That's the intercept, right? So what you are seeing here is as the material gets soft, even for a little stress increase here, it's taking a big hammering. Does that make sense? So that's what I want to highlight, is that P is not necessarily, man, I broke another one. I'm on a roll. They're going to charge me money now. What I'm trying to say is, depending on the material and the stress state combination, it can be very different. The effect. This one. This is sigma level, sigma D. Okay. Sigma D is 15, 30, 50, and then this is 60. Okay. Look, 15 to 50, you did see a little bit of increase in strain, but not something that you should be worried about, or not something you should be panicking about. But look at what happens when you 60. So that's what the boundary is. You are going to go high with respect to the subgrade stress ratio that your material is just going to collapse. Remember, resilient modulus is a characterization test where we are intentionally applying stress states that are very, very low compared to shear. Rutting or permanent deformation is something where you are you're trying to challenge the material to say how not keeping it very low or something. We are pushing it, right? We are saying where are you going to collapse? That's my rutting behavior, right? This again is the same thing. QU, remember I said 50 to 60%, 60, 70% you can be high. In this data, it's about 50% of QU, you are fine. You go to 75%, you go to 100% and stuff, collapse. How repeated loading you're applying and stuff, right? So the whole idea is, it's a pavement. Remember what I said at the very, I think day 2 maybe or day 1. I said when you track critical pavement response parameter, you all gave me vertical strain at the top of the subgrade, and I say I personally believe in vertical stress more than strain, and we'll see a little bit more in a few slides. But this is the reason, because the stress directly compares to strength. Cutting is governed by strength. Cutting is, so now the question is, what would you rather correlate CBR with? I would rather correlate CBR with shear strength, which would give me an idea of the resilient modulus, because modulus is not a teaching kind of a behavior. Modulus is not a torture test. Modulus is not something we are trying to get. That makes sense? So this is a clay material. There is a clay versus silt. The clay has a higher unconfined compressive strength, and how the behavior changes again. 75 to 100, it just collapses. Another data set, I'm just going to skip this one. This one is again SSR, the same stuff, subgrade stress ratio. 1 means it's equal. Look what happens. Collapses with load application. Only less than 60, 70 load applications, it's gone. Material collapses because you are demanding way too much of it. You stay lower 0.25, 0.5, 0.75. We're okay. We're still 7.5. The reason we advise not to go to beyond 7.5 is it's only 1,000 cycles. If you look at make it 10,000, you'll see actually it probably goes very high or even collapses at the point. Here you're in really, really safe range. So designs and stuff, any material being tested, the stress is low. That's the whole concept of protecting the weakest layer, right? Rutting is a good representation of protecting the weakest layer, right? This is, you already saw this. This is sigma d over qu, less than or equal to 0.5, 0.6. This is what I said. You keep it in that range, you'll be fine. And this is C is the cohesive. There's nothing new here. This is an effect of moisture. Now we are talking about the same material, but now whether the person slept at night before or was partying drunk the night before, right? So 30%, the same material. We are still maintaining subgrade stress ratios and stuff. Look, at 0.25, it's not a big problem. 0.5, it's not a big problem. 0.75, now the material is so much weak that the 0.7, it's actually starting to collapse now, right? Moisture effect is very bad. Effect of W, again moisture content. This is optimum. This is optimum plus 3%. This is optimum plus 4%, right? So where do you compact your material? Again, we don't in this course, but you know that in the bell-shaped, same density at 2 water contents. Where do you compact? The dry side or on the wet side? Well, depending on what compaction theory you're going. If you go by the lubrication theory, right, then you're not talking about flocculation versus dispersion and stuff. You're just talking about strength. It's more things, right? It's stronger. Can you think of one example or one case? And you all should do this. Actually want to compact on the wet side? Say again? Why? To reduce the permeability is yes, one reason. Let's talk pavements. Yes, on the wet side you have reduced permeability because you have more water. Pavements, when do you compact on the wet side? When you have a material that is very, very sensitive to expansion and stuff with higher water contents like expansive soils and stuff, it is not uncommon to actually almost flood it or compact it on the wet side. Make it expand as much as it wants. Take care of all the expansion and then somehow with a geomembrane or something prevent further moisture changes and stuff and build on top of that. You don't really want situation to be happening. It's very limited cases, but yes, permeability can also be another case. Okay, this is again moisture content. you know, at lower moisture content it is 23 is good, but beyond at one point it like 26, 28.5, 30.5, it was kind of similar and stuff. This is freeze thaw cycle. Okay, another very important thing that you should pay attention to. Freeze thaw cycle collapses the internal void structure of a clay, of a soil, and it actually becomes very, very susceptible to failure and permanent deformation. So the same material, okay, no freeze thaw cycles. Look at the rutting. One freeze thaw cycle. No, what? Yeah. Sorry. Yeah. 15 is the sigma d. 15 is the sigma d with no freeze thaw cycle, and 30 is the sigma d with no freeze thaw cycle. So this is not exposed to freeze thaw. From 15 to 30, look at how much increase you have. Here, one freeze thaw cycle, 15 to 30. Look what that would do. Same soil, same material. Just one freeze thaw cycle collapses the void structure completely and the soil matrix, and you just become much more susceptible to. How much does water expand when it freezes? Come on. %9. It's a trivia I asked all the time in my class. I thought you guys will know this. Okay. Subgrade soil. Okay. Now, let's break now. This is a good breaking point. We have 3 minutes, or we can have 3 minutes of discussion. But because this is the very important concept of using resilient strain to predict permanent deformation. Remember, that's what we were talking about, like strain on the top of subgrade, and why I said no. It's going to take some time. So it's a good natural breaking point, but we have 3 more minutes. So if you want to, any questions, address during that time. It's not 0.06, 0.6, 60%. Don't apply more. Can you? Here? There is a point here. That's 1.00. So this is equal, and then this is 50%. 60% is somewhere here. So for repeated loading and stuff, 6, if you have a low volume road, go a little bit up, 0.7, not more than that for sure. 0.65, not more than that. Any more? Anything else? Yes. Well, if it's an unbound material and if it shows stress behavior, maybe yes. Now wrap has some funny properties sometimes. Like wrap, it's very interesting. Sometimes if you do resilient modulus testing, wrap will give very, very good numbers. But if you do rutting testing, wrap will actually give bad numbers because the asphalt kind of lets it collapse a little bit more and stuff. So how is it captured? You'll just have to study. I mean, I don't think there is any theoretical answer to your question. Yes, for everything morphological properties affect, right? That's what the angularity index, the surface texture index and everything, that's what it was. So yes, if your material changes, like for example, slag 1 versus slag 2 or aggregate versus slag, so now you are not just changing the material, you're also changing the angularity, you're also changing the surface texture and stuff. So you have to have some way of normalizing it or trying to balance it out. the models consider the role of stress history. In the resilient modulus test, no, right? It's under the given sequence and stuff. And stress history, yes, it's very important. But in the resilient modulus, we are talking about just initial shakedown or stabilization, and then we are going into resilient. But stress history becomes very important in permanent deformation, right? But to answer your question, no, there is no stress history consideration. Just there. Let's break 15 and then we'll Thermal Dakidia Pilam. Okay, let's get started. Others will come, but we need to get started. So this is the stopping point where we decided, and the whole concept of this goes back to the first day when we talked about uh, resilient or elastic strain on top of the subgrade being the one of the critical response parameters that is going to predict your rutting. And I did mention something on the first day that all our pavement analysis programs that you see in practice, 99% in the research are all elastic programs. So what you get are elastic responses, right? So you're talking about elastic strain being predicted, computed on top of the subgrid, and you are using that to predict rutting, which is a completely plastic phenomenon, right? So this is a test result, and the x-axis is epsilon r, or resilient, elastic, you can call anything, right? You know, because resilient response is essentially elastic response. So you have that, and epsilon p at n equal to 1000. So it's basically plastic strain for the same material at n equal to 1000, right? And if you see here, as the CBR of the material changes for the given resilient response strain or elastic strain, you can have multiple plastic strains. Does that make sense? You have, so the different lines are for different CBR, same material, and you are subjecting it to the same amount of elastic strain, let's just say 0 point whatever, 22 or something, whatever it is, percent. As you can see, it intersects all these 4 lines at different values of epsilon p, right? What that means is that as the strength of the soil changes, the same elastic strain can lead to different plastic strains, right? That is the reason you would rather have a CBR relationship to epsilon p rather than an epsilon r relationship to epsilon p. So this all boils down to the argument that don't just use elastic strain to predict rutting. Now I said CBR. What is CBR? A strength index. What is best correlated with strength index? Some kind of a stress, because stress is nothing but value of stress it can take, right? That is the reason behind the entire argument of why stress on top of subgrade is a better indicator of strain, permanent deformation, than strain on top of the subgrade. Granted, if you run a plastic analysis, then of course strain is the best, because strain directly is your permanent strain. But you are doing elastic strain, right? So that is the entire reason we actually vote for saying that rather use a strength and stress kind of a prediction approach rather than using a elastic strain. That's the reason when you track critical pavement response parameters, track the vertical stress on top of the subgrade, not vertical strain on top of the subgrade. Capture the stress, then compare that to your unconfined compressive strength, your shear strength, whatever you have CBR, compute an unconfined compressive, do something, and then you can have a ratio and stuff. That's what your sub SSR is. So this is a very important thing. Let's also take a look at that. Limit epsilon r and epsilon p will be okay. That has been the understanding for a long time. Limit resilient strain or elastic strain and permanent will be okay. But look at some of the different algorithms. There is Asphalt Institute, there is TRRL, which is in UK, there is Belgian research and stuff, and there is actually this is the model. Epsilon v vertical is L 1 over n to the power m, very similar to a n to the power b, very similar. There's no, I mean, just model different, little bit of a different, but look at how different the model parameters can actually be. So you have similar values. The rut depth is 0.5 here, 0.4 here, 0.8 here, right? So similar kind of resilient strain measurements or thresholds are leading to different values and stuff, right? So it's not a very good approach. Look here, micro strains, allowable micro strain in the subgrade, AI and Shell, Asphalt Institute and Shell, n equal, this is the number of ESLs, number of load applications, basically it ends up 5 million, 10 million and stuff. You have allowable strain is 799, Shell says 1575, 478, 885, 286, 498 and stuff. Because epsilon r or epsilon e, whatever you want to call it, elastic and plastic, it's not a unique relationship. It changes when your subgrade strength is changing, right? That's the reason track stress, that's a lot better because you can compare it with strength directly. That's essentially what the bottom line is. So for epsilon p is 2%, which is this graph, what are allowable sigma d and mr pairs? Okay, think again, I am allowing epsilon p is 2% permanent strain, plastic strain. What are my allowable mr and sigma d pairs? What it's saying is, if mr is 14,000 psi, your sigma d should be about 20. If mr is 75, your sigma d should be whatever 100 divided by 6.89 or whatever that comes to be and stuff like that, right? So your epsilon p you can limit, then resilient modulus and sigma d it has to shift based on the resilient modulus. Okay, again, why are you going down to? You're actually going to dynamic deviator stress, you're going to stress. That's how you're limiting your numbers. Okay, now comes the rutting model in MEPDG. Okay, this is the scariest looking model that you will see, at least in this short course, right? And it indeed is very scary, okay, because it has some models, some resilient strains that you get, some epsilon 0 which is a material property. There are some there is vertical strain that you actually calculate using the layered elastic analysis and stuff. It actually came out of, again, Professor Litton's group back in 1989, and a version of that was adopted into MEPDG. The major difference is in Professor Litton's model, his model parameters like epsilon naught b and sigma rho, they were only dependent on stress. But in MEPDG, there is other material properties that are included here as well to predict. Okay, the MEPDG model is quite complicated to understand, to implement and stuff. And also, if you go into the details, so there was a proposal we were working on back in 2014 or something, and uh, I was the postdoc, so I actually was doing all the work. I actually went back to Professor Chuck Swartz, who is now retired. I mean, he retired from Maryland. He's now teaching in a university. He was actually the behind the entire unbound material part of MEPDG. He was back then in Maryland, and he used to work with. I mean, he was collaborating with Professor Matt Witzak. So Swartz was a part of the proposal as well. So he helped me understand how the heck this thing was developed, and track it down. Bottom line is, once you go really into that appendix, I think it's GG or something, I don't remember anymore, it's been more than 10 years. When you go into that, you will see that you do all these calculations. At the end, there is a assumption there saying that just because we saw in Asho road test that 70% of the rutting was coming from the unbound layers and stuff, anything that is happening, we're going to just throw a 70% number and we'll just call it good and stuff. So what I'm trying to say is there is a lot of complex mathematics happens, and then in the background there's a little bit of cheat happens to go. That's essentially the shift factor and stuff, right? So for all honesty, calibration of this based on your material for MEPDG implementation has pretty much been impossible and stuff. There is I'm not familiar with anybody who has actually done this entire calibration and stuff. So what I'm going to do here is I'm going to say a couple of these. Oh, by the way, this is aggregates again, AN to the power B, and remember how we focused on SSR, subgrade stress ratio. Here we are focusing on sigma 1 over sigma 3 because there is no QU in here, right? So we'll do that. But what I'm going to show you is another approach, which I think I shared that paper with you. If not, I think I did. I'll show you that. And we proposed a model about 10 years back, which does a much better job, at least in our view. Couple of things. AN to the power B. What are the factors that are considered? I told you A is related to magnitude of permanent deformation at first cycle. That's what's written over there. You remember that. And B is the rate of permanent deformation. It's the strain rate. If you do a differentiation over there over N, you'll see that that's what B is basically, right? So that's what A and B values indicate. And there is another model. I don't know how to say his name. I have always said it Kedder, but I don't know if that's the right pronunciation. But they also propose something called a strain rate model. So they are predicting absolute strain per every cycle. They are predicting strain rate per every cycle. So d epsilon over dn, rate of accumulation, right? So obviously go down, right? Because when your curve becomes flat, your rate is going down. It starts at a very high value, it keeps going down. That's what this rate model is. Okay, in the Asho road test, again rutting, this is what I was trying to say, delta AC plus delta granular plus delta sub base, and you can actually calculate the strain rate and stuff like that. This is again for unbound granular materials, how the Seng and Litton model and how MEPDG model is. Okay, so this is what I wanted to go, checking the accuracy of the MEPDG model. This is a paper we wrote back in 2014, I think, or 15, I don't remember. Liang Chow was a master student. I was the postdoc and Tutumler. So we actually developed a model. The name is actually CMT, Chow Mishra Tutumler, and we actually proposed how to study the rutting in a better way, more representative way than what the MEPDG was doing and stuff. So let me show you what this was. Okay, 2014. So what we did is we took like a standard pavement section, and we had test results for all the layers, shear strength and permanent deformation, resilient modulus, all materials we had tested, and we simulated pound wheel load with 80 psi tire pressure. 80 psi would be 550 something, probably 560 close kPa, right? And then MR varied with aggregate type, and we took a mu of 0.4. Subgrade layer we just simplified because it is, we were trying to simulate MEPDG, so we said 55 CBRS plus 0.64. We didn't do stress dependent, right? And determine aggregate resilient modulus from repeated load permanent deformation. Like when we had a little bit of a stable behavior, we would take the resilient strain, we divide it, and then we take aggregate modulus, and then we analyze the same pavement using MEPDG. So we basically put in MEPDG to analyze what it is doing, and we actually knew how much it is performing in the lab, right? So the whole idea that we saw is material G1 was here, and then all the other three materials were over here at the top. They were kind of merged together. G1 was the low, then G2, B, and L, they were all at the top. And if you look at it, G1 is 31,000 psi, and this is 21,000, 20,000, 20,000. So if you look at it, the MR values for the three materials are very similar. Rely on resilient strain to predict permanent deformation. Obviously, if your resilient modulus values are similar, it's going to predict a similar value. Right? That's what we saw. But then there is a different, we plotted against sigma d the 10,000 cycles, and then as you saw, this was here, material L was over here, material G2 was over here, material B was over here. So it's very, very different permanent deformation strain patterns. This is actual lab data. So we are like, why is this not being reflected in your MEPDG? If your material is so different, MEPDG is just because the resilient does not mean permanent deformation should be similar, because it's elastic versus plastic. So then this is the model we proposed. We said a n to the power b, and we are going to include sigma d in there, which is deviator stress, and then we said something called tau f over tau max, and this is what I was saying we're going to dive deep into in this session. What is tau f over tau max? Okay, I think the best way would be, no, I think I can do it here and the board. I don't need to switch. Look at the Morse circle. It looks scary, but it's not very scary. You draw the Morse circle, right? And then because you have the shear strength test, what did I say? Cutting is related to shear strength, not resilient modulus, right? Shear strength. If you have shear strength, you can calculate the failure in inclination, right? 45 plus phi over 2, right? So that's what this is, 90 plus phi, right? In Morse circle, everything gets doubled, remember? So 45 plus phi over 2 is basically 90 plus phi. So when you plot that, and then you calculate tau f and tau max. So let's try to decode this. What is tau f and what is tau max? Tau f is the shear stress on the failure plane, right? Tau max is the shear strength of that failure plane. Like when tau f is tau max, what has happened? Failure has happened, right? So do you see how it is similar to sigma d over qu? It's very similar concept. Instead of doing a normal stress sigma d over qu, I am saying I'm going to take the failure plane, measure its shear, and then I'll compare it to the coordinate of the Mohr Coulomb failure envelope. That's my shear stress ratio, SSR. Remember I said today SSR can mean two things: subgrade stress ratio or shear stress ratio. So this is what we did, is we said it's a shear stress ratio, and we actually incorporated that into the model. Okay, we said it's not just a function of the deviator stress, it is also a function of the strength, right? Just stress is 100 kg does not mean everybody will collapse. I will collapse, but a bodybuilder probably 100 is nothing for them, right? So that's the reason we incorporated this model into this parameter into that. We said we're going to consider not just stress state, but also we're going to consider strength in there, right? So then we modeled it, okay, and look at the actual performance and the predicted performance for different shear stress ratios. So in the repeated load triaxial testing, we knew the strength, we applied increased the deviator stress targetly so that we can target different tau f over tau max ratios and stuff, and we went all the way up to 0.75, which is bad, right? So you have 0.25 pretty flat, 0.34, 0.5, 0.75, it's getting progressively bad, right? So this was actually a pretty well received paper and a model that where we proposed, saying that no, we are going to not just rely on the MEP-DG model, which relates on resilient strain, we're actually focus on stress instead, stress and strength, and then just use the basics of Mohr circle. So this scary thing is nothing but the sigma f. You can do it. You can do it analytically. It's just trigonometry right there. Nothing special. Okay. So then we can look at some field permanent deformation results. This is in the NAPTF that I said, National Airport Pavement Testing Facility, and flexible pavements 5 to 10 inches of AC, CBR 4 to 8, and foiled with up to 4-inch strut. Highest contribution is often in the base layer and stuff, which is P209. So at major contribution at wheel loads of 45,000 to 50,000 pounds, which is typical for aircraft. Now we are talking about big aircrafts, right? This is airfield pavement, not highway pavement anymore. So you are now talking about major contribution to permanent strain actually coming from the P209, which is the base, versus when it increased significantly more, then your subgrade was contributing more. So what I'm trying to say is the depth, at what level you are failing, or how much is your rutting. Can you isolate your base versus grade? At some levels, base will be much higher. At some levels, subgrade will be much higher, right? So it can change. So factors affecting delta P, primary factors, sigma D, epsilon, sigma 3, and the ratio and strength and tau max. So we added those and saying that what is the maximum shear stress that is applied on the failure plane, and the tau over time max, and number of load cycles. Secondary factors, dry density. Now density is a very interesting thing that has helped us, escape or cheat for a long time, right? Because density is not a mechanistic input. None of your designs require density. Well, some analysis may require because they want to calculate. So H, the only role that density plays, and surcharge is very small anyway. But the good news is that in a lot of ways, density kind of correlates with strength and stiffness, because better packing leads to better performance and stuff. The problem arises when you have something like railroad ballast or open graded aggregate, where density just cannot be established. It's just not possible. There is so much void, you cannot stick a nuclear gauge in it and do it. It's full of voids. That's when you run into challenges on how to do this. Percent crushed, uncrushed versus crushed stone. This is actually something Dr. Sahu was just mentioning over T. me that some of the material in bases here can be pretty flaky and stuff if there is no quality control and stuff like that. That can be very challenging, right? Because flaky material, what's the main problem with elongated material? They're going to break, right? So whatever you have done, whatever density you tested or measured, it has now changed because the material has changed, right? So your packing has changed, your orientation has changed, and now you can have really big problems. Fines content, as I said, fines and permanent deformation have a very interesting relationship. When fines are optimum and they are dry, the system actually behaves pretty stable, because the big rocks, the way I explain it in undergrad classes is, imagine this room full of basketballs. Okay, now throw in a few tennis balls in. Now throw in a few table tennis balls in there, right? That's a well graded system or something, like different representation and stuff. What role do the tennis balls and the table tennis balls play? They stabilize the matrix, right? They fill the voids. The big balls are not moving widely and stuff with a little perturbation and stuff. The problem happens when there is water. A high fines material can just collapse with water, because water plays the role of, or makes it like a slurry. Basically, it's a lubricant now. Now you have greased the contact points and stuff, and they're going to just slip past each other, right? So the fines is a very, very tricky concept, right? Where you start. Important if fines, moisture content, this is very interesting. Moisture content is important if fines are greater than 12%. This is actually one of the findings of my dissertation, my PhD work is I separated different bins and we did them manually. 0% fines, 4% fines, 8% fines, 12% fines, 16% fines. What we saw is, when you have less fines and you add water, water just drains. So your fines are not really hurting you as much. The problem is when the fines cannot escape and the water just wets them, now makes it a slurry. That's when the problem is. Now the system collapses, right? So it's very important to realize where it is. And then I think you just asked stress history effects. Stress history is very important for permanent deformation. How do I explain stress history? Let's just go back to our weightlifting thing. I have never lifted a single weight in my life, okay? Like for weightlifting, I may have done some exercises, but never have lifted weight. Now if I go and on day one lift 100 kgs, it's going to break my back, right? The way to start is 20 kgs, 40 kgs, 60 kgs, 80 kgs, 100 kgs. You build it up. Stress history is exactly the same. If you build up stress history slowly, then aggregates will actually resist quite good and stuff. If you go from the top to the bottom, it just falls apart, right? So it's the packing that is very important. I think we talked about this already, the tau f over tau max. Again, you're asking about the ratio, 0.6, the magic number. Keep that below that, and you'll be fine with rutting. And anybody doing triaxial tests in your labs, you can try this out. You can just set this formula, set it up, calculate, do a shear strength test. By the way, so many people doing resilient modulus tests. How many of you have actually done shear strength tests on aggregates? That's not good news. You need to run that, right? Shear strength, first thing, it's very difficult, I understand. Resilient modulus is easy to play with, right? Stresses and stuff. Shear strength is difficult. But the strength, actually, and when I launch PiliPave today, you will see why strength is important. You can actually cut off the stress distribution. Actually, it's beautiful how Professor Thompson imagined this. The way the software works is at any node, if the stress actually increases the strength, he actually collapses that and he redistributes, saying that this element does not exist anymore. It's not going to take any stress because it is, the stress is more than the strength. So he actually redistributes the entire thing and stuff. It's beautifully imagined. I don't know how to do it mathematically. CCP tests, 9 psi, 15 psi, 21 psi, 27 psi. As the at confining pressure 3, you just, this is a sigma d over sigma 3 of 9, sigma d over sigma 3 of 3. As the deviator stress increases with number of load applications, the permanent strain increases. This is confining pressure effect. Okay, axial permanent strain. Let's just say 0.6. Let's fix a 0.6. When sigma 3 is 3, you are only taking 25 psi. When sigma 3 is 8, you are taking 45 psi. When sigma 3 is 10, you are never hitting this. That makes sense? What does that mean? The tighter you hold, you look confused. This is, pick an axial strain. Let's just say 0.4. For sigma 3 equal to 3 psi, at 15 psi deviator, you are hitting 0.4. At 5 psi, you are hitting it at about 20. At 8 psi, you are hitting it at about 35. At 10 psi, this is kind of higher than that. I don't know how that works. But you never even get there or something. So what essentially is the tighter you hold the material, the greater stress it is able to take before it accumulates some permanent strain. That's the saran wrap example, right? The kitchen wrap, and with your marbles and stuff. This is sigma 1 over sigma 3. Again, tau f over tau max is a little bit of an advanced way of looking than sigma 1 over sigma 3. Similar stuff, right? We're not talking about shear or shear plane now, we're just talking about principal stress ratio, sigma 1 over sigma 3. Here, look, 30 over 15, 20 over 5, 30 over 5. This is sigma 1 over sigma 3 is equal to 7. Okay? This is sigma 1 over sigma 3 is equal to 5. No, 4. Sigma d over sigma 3 is 4, but sigma 1 is 5. The ratio, right? So what this is essentially saying is you have very, very high confining stresses here with respect to this, and then the ratios, as you keep changing, they're also sometimes how much confining, how much stress you are able to withstand and stuff, it can change based on the material and stuff. This is sigma 3 is 10 psi. This is actually Dick Barksdale. This is my advisor's advisor, my academic grandfather, 1972. My academic grandfather's grandfather or somebody like that is actually Terzaghi. I actually have a lineage, academic lineage tracked over it. So soil, Terzaghi, right? The father of soil mechanics. So yeah, I come from royalty. So this is Barksdale's work. This is n is increasing, and as you have sigma 3 is equal to 10, this is sigma d over sigma 3 4.6. As you keep increasing, your epsilon p increases. Very similar to tau over tau max. Very similar, but on different terms. Stress dependent Roding models. What are the different Roding models available? There can be again just a sigma 3 to the power b n to the power c. This is where you are only including the confining stress, right? This is only the deviator stress. This is now the deviator stress ratio. This is now deviator stress, and this separately. This looks very similar to that a version of the Uzan or the Pezos model, basically the UT Austin model and stuff, where they have actually sigma d and sigma 3 separately and whatnot. And then you can actually do rutting model parameter A as a function of deviator stress. Remember, one of the major criticisms of the phenomenological model is that it does not take into account stress. But the defenders of that, or who believe in simplification, they actually say, look, if I apply deviator stress and plot A, I get a 0.97 correlation. So A is actually directly affected by stress. So even if you don't have it in the formula, it is indirectly in there, right? It's not the end of the world. This is actually some shakedown work, people who work on shakedown. This is very, very relevant, folks. Why? It's because the load level does not necessarily stay the same all the time. It can increase. One example is actually in the railroads, right? In the railroads over the years, they have actually increased the axle loads and stuff like that, right? And as you know, tracks don't get reconstructed very often. I mean, tracks are very, 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 very long standing and stuff. So what you can do is you actually stay there, and then you can, now your sigma d is all of a sudden greater, and you see significant difference. This is the collapse phenomenon. Look, this is 63 kPa 0.5, and now this is 336 kPa. It increased significantly, but look, it actually goes over here, and then when you increased it, now the gap between the two is also significantly greater, right? That's basically saying that just because under one stress state it was behaving similarly, when it changes it may not. What does this mean? It means that if I'm running a 100-meter race with somebody, maybe I'm close to that person, but the moment it becomes a 800-meter, I probably never finish, right? So this is stress, that's stress dependency, right? Just because you see something, that's the danger of extrapolation. You run this test and you're like, oh, the materials are different, go use it and stuff, and then like, what just happened, right? Because that's stress dependent material. You don't extrapolate. This is related to, I think, again, you were asking a question about the morphology of the material and stuff like that, right? What ranges? No, but here level has changed. This is not repetition. What he is referring to is this lady called Sabine Werkmeister. She was from Germany, and she did some pioneering work on shakedown theory of aggregates and stuff. And that's what he's referring to about her ranges. She says like range A, range B, and range C of behavior and stuff. But I think what you are confusing is, your statement would be true only if the variable here would have been n. Look, here the sigma has changed as well, right? You are talking about just based on n if it is changing, and that happens too. That happens too. It's all, remember I said, not fatigue can be picked up as fatigue related. Like even if it is not, load law is not changing, just repetition can sometimes collapse your material. You can just go. That's one aspect. You're talking about phenomenological as well, like slag and all of that when you march. Right now you're talking about angularity changes, surface texture changes, packing changes, right? This is, whoa, okay. So this is actually something called the University of Illinois Aggregate Image Analyzer that my advisor had built. He has now built something called an EUIAI, enhanced in University of Illinois. But anyway, The bottom line is it is a set of cameras, 1, 2, 3, 3 different views, takes pictures. It's actually a treadmill. This is a treadmill. It runs very slowly, aggregates pass on it, and the cameras keep capturing, and a lab view code just goes and calculates the AI. It's image thing. These days you can do it in 15 days probably. What these people did as their dissertation, because these days it's becoming very, very easy, image analysis. It's actually, one of my students, I was so proud of her, a master's student. She was doing some discrete element modeling, which happens to be another one of my mentors. We're not going to go into that. I told her, I said, I want you to capture this unbound aggregate shape and import it into DEM. She's so resourceful. She went to Autodesk and found a version of a student software. I don't remember the name. Autodesk is the company that makes AutoCAD. Autodesk found some kind of a free version for students, used her cell phone and like just as Android, just took pictures from all around and then imported into that software, and within 4 hours she had that image for me completely digitized and quantified and stuff. Like, here is your image. Talking about a master student, I mean, I was blown away. So what I'm saying is these things can be done very easily for you now. I mean, you can do it. You can just capture images, use some ready-made Python algorithms to detect edges and stuff and quantify what is known as angularity. Bottom line is, as angularity index increases, friction angle increases significantly because it's an interlocking, right? And if friction angle increases, what are you increasing? Your tau max is increasing. So for the same stress state, tau f over tau max is now very, very low. So now you are completely stable, right? So hence the importance of quality control. Hence the importance of at least this many crushed edges and stuff like that. It's not just garbage, it increases strength significantly. You need to remember that. Right? Effect of density, okay, depends on what kind of material you have. Okay, if you have 90 PCF, 96 PCF, 99 PCF, number 4, it's a number 4 stands for ASTM number 4 gradation. You can look up ASTM number 4. Oh no, sorry, this is my bad. This is ARIMA number 4. It's not ASTM. This is railroad. So it's relatively open graded material. If you density, if you pack it better, your permanent deformation becomes very good. Hence the importance of compaction, right? Again, remember I said railroads and pavements are very similar. I don't know how many of you have seen railroad construction track. Do you know what a track stabilizer is? Has anybody heard of it? Okay, so you know what a roller is, right? A compact, like a steel drum roller. You've seen that very, very common, very often. Your steel drum roller is something that you use on pavements all the time. On railroads, there is nothing called a steel drum roller. You're building a track, and ballast is actually not really compacted. So what they use is something called a DTS, dynamic track stabilizer. It's a train. Remember, I don't know if you know this, but railroad tracks are constructed using trains. Trains actually construct themselves. So basically, all the track are trains. They're not like coming from the side or anything. They lay something, they go, they lift themselves up, they put it in. It's fancy. It is cooler than heck, if you want to see. So DTS is a train, basically like a vibratory compactor kind of a train that actually vibrates the track and stabilizes it, right? And if you do that, and it's very difficult to do, and especially people get scared when you are near a bridge or something, because you can have resonance and the bridge can collapse and stuff if you're not very careful and whatnot. Yes, can work up to a certain point, and then at the bridge location they kind of get off. They're like, oh, I'm not going to vibrate this anymore and stuff, and that is where all the problems start, right? So it's compaction, very, very, very important. Fines. This is very interesting, like fines, yes, increase number of percent of fines, it increases, epsilon p increases, but as I said, the effect is lot more. This is my work, this is 27.1. This is what I was talking about, 16% non-plastic, 12% non-plastic, 4% non-plastic, 8% non-plastic. So above 12%, because it is optimum moisture content, it's not dry, it's like there is enough water. So when you go above 12%, the permanent deformation starts increasing significantly, right? This is what I was referring to. This is another one. This is, look, plastic fines. This is plastic, 90% weight of optimum. It's on the dry side, but plastic on the dry is actually worse than non-plastic on the wet. A lot of times plastic fines are very, very slippery, very sticky and stuff. So this is all, constituted samples, manually blended and stuff. Look here, G is gravel, and this gravel is uncrushed material. Okay, what is special about uncrushed material? They are kind of spherical, right? If it is spherical, what is the void space? More or less than crushed materials? How much? What is the most efficient packing you can have among particles? What shape? So I'm talking material science now, I'm not talking civil engineering. But you never have cubes sitting on each other, right? Is it angular or is it spherical? Where is your, what minimizes your volume, voids? Spheres. Spheres minimize your void. So uncrushed material actually has less void than a crushed angular material. Okay, so when you have 12% fines in less, it actually more full than 12% fines in a greater voids, right? So the gravel at 12% actually collapsed, whereas the limestone and dolomite were crushed at 12% did not collapse. It's about how full you are. It's all about voids. It's all about void structure, right? That's very, important. Stress history effects. Okay, low sigma to high sigma, epsilon p is very low. I told you this already. Gradually lift weights, your collapse is going to be much lower. High sigma to low sigma, epsilon p is very high. If you start with a very big one and then you reduce and stuff. Okay. Now do you realize why in the resilient modulus test in the aggregates it's actually increasing orders? Right? You're actually trying to systematically apply more and more load. This is stress history effects again, loaded at 20 and 1 kPa confining and 336 axial. So specimen conditioned at, this specimen is conditioned at 21 kPa confining and 336 axial deviator stress right here. And this specimen is 21 kPa confining and 105, and this is unconditioned specimen. Okay, so when you don't condition it, apply everything same load, it's going to, you have to condition. That's the stress history effect and stuff. This is, if a model does not consider the effect of stress history, the trend is quite different from the measured one. If you don't measure, like, this is important, folks. What stage are you trying to model? Are you only trying to model this portion without considering how it went? Right? So if you are trying to develop a proper model for all different stress states and stuff, you have to consider different stress stages and stuff. Design concepts, rutting due to base compaction and rutting due to shear in base. This is two different things, compaction versus internal shear. Compaction is good, you're just compacting, just means that you didn't compact very well, right? Shear is different. Now your tau over tau max is a problem, right? So tau max increases, epsilon p decreases, tau over tau max increases, epsilon p increases. I told you this already. Right? When your angular material, your strength increases, so your tau max is increasing, so your permanent deformation is very low because you're at a lower level, you're playing at a lower percentage and stuff like that. This is shakedown stuff with the whole idea of how shakedown happens. There is first step, it's called plastic shakedown. Then slowly it increases to what is known as plastic creep, and then there is a stiffening response, and then what is known as incremental collapse. So just the same load, unless it is very, very low, if you just keep applying and applying and applying and applying, at one point it's going to fail. Okay, now we're not going to go into deep into this. This is the ABC stuff I told you. This is the Sabine Werkmeister I referred to. This is her dissertation work. Need for advanced research on delta P. You have some data, but then beyond that, future large generation aircrafts and stuff like that, you don't know what the load is going to be, right? Why do you need that? Your pavements, you're going to use recycled materials, you're going to use other kind of materials. You have to study mechanistic methods to do this. Okay, this is some shear concepts. I'm trying to switch. We talked about principal stress rotation. I want to show some stuff related to railroads. I'm going to switch now to a railroad related presentation to show you what is the role of permanent deformation and shakedown and ballast layer and stuff that you should be careful about. This is a presentation I just, I decided to do this last night because I wanted to show. So this kind of now starts a little bit on the research side of things, but I wanted to highlight this thing for you. This is my postdoc work. We used something called MDDs, or multi-depth deflectometers. Okay, so what is an MDD? Everybody knows what an LVDT is, right? Now imagine an MDD is basically a series of LVDTs, but they are installed at different levels inside the track. So we actually drill and then we insert it. So the first one is at the tie ballast interface, second one is at the ballast sub-ballast interface, then third is at the sub-ballast and fill layer interface, 4 is here, 5, stuff like that. So you just insert. How is it installed? We can talk later. I want to I may go through this presentation again tomorrow with the sense. Today we are going to focus on material behavior. Okay, so you'll probably see this twice. So this is all us installing and everything. This is how it works. I'll explain all of this yesterday. That's me. This is all us installing in the track and stuff. This is another side. That's me again installing, and this is the boring logs. Again, we're going to look at instrumentation stuff tomorrow, not today. This is all us installing and putting. That's again me trying to install. That's me collecting data. That's under the train and blah blah blah. Okay, this is analysis of occurred data. So this is what I wanted to show: permanent deformation accumulation. Okay, look at this. So the way you want to understand this plot is every sensor gives the deformation of that layer only. How I'll tell you tomorrow. Okay, 1 is only ballast layer, 2 is only sub-ballast layer, 3 is only 5 ballast, 3 is sandy loam and stuff like that. Look at the permanent deformation. This is data collected over 550 days, which is 1.5 years, right? So I used to go, so this is where I used to be more of an Uber driver than a researcher, because my base was in Champaign, Illinois. The site was in Philadelphia, Pennsylvania. It's a 13-hour drive, and I got so used to it that I'll get up in the morning, 6 o'clock, start driving, reach there 7 o'clock at night, non-stop. Myself, nobody else, and then just collect data the next day and then come back and stuff. So anyway, look at this. With time, this is a track transition. This is a bridge approach. Remember I said how at bridge approaches don't compact very well because there is many challenges and stuff like that. Look at the permanent deformation. So this is LVDT1, which is the ballast, the top layer. Look what happens. What is going on here? Say again. They resurface the track. Like in railroad tracks, it's not an overlay or anything. It's in that. It's called a tamping operation. It raises the track and it fills it with ballast and stuff. And when it raises the track, my sensor also got lifted, right? So that's the negative. It goes up, and then again starts collapsing, right? So this was a 3-year, $1.6 million study that, my advisor was the PI, but I was the lead researcher on this one. And honestly, this project is the reason I have an academic career, because my PhD was very ordinary. I'll tell you from now, very openly. I was not, my research in PhD was just okay, nothing standing out. But this project is what propelled us to the things like, because nobody had done this in the world, and we did this, and we actually identified that permanent deformation that you see in railroads, it's this much is coming from ballast. Everything else, look where they are standing, almost negligible. So it's your rocks that are rearranging and stuff to cause all the track defects and stuff. And there is a big problem with railroad track, right? If a pavement has a big bump, you are interacting or hitting it with what? Tire. What is the tire? What is a rail? And what is it riding on? Steel. So a steel to steel bang is a lot worse than a rubber tire to an asphalt pavement bang, right? That's derailment risk and stuff. So that's what we found on investigating. So the project's name was investigating the root cause of what is known as differential settlement. The problem is very commonly known as bump at the end of the bridge. You probably have heard it. The way I explain it when I give talks related to this to students, I say, a friend of yours is driving and you are in the car closed. When they go over a bridge, you always know, right? Because when they enter the bridge, there is a duck duck. When they get off the bridge, there is a duck duck. Where does the duck duck come from? It's differential settlement. There is always an elevation difference. Why does that happen? Because the bridge is standing on deep foundations. It's going to rock or something. It's not settling. And your approach is a fill layer or something, either an embankment or something like that, right? And that's going to settle with time. That's the permanent deformation. That's rutting, right? So that's what I wanted to show you is MDDs. We actually measured this. This is another site. Again, only after about 34 days or something, or 20 days, they resurfaced, and then they came back after about 375 days, they resurfaced and stuff. Look how robust and resilient these instrumentations are. They actually stayed there irrespective of the maintenance and stuff, and they were giving us data and stuff. So this is transient. This is permanent. What about transient? Transient is basically, I don't call it elastic, I call it transient, because I don't know if the transient is 100% plastic happening there. What I'm measuring is transient, like a live So this is when I used to go sit down on the side of the track with my laptop and in an instrumentation van, and then we would collect data under train loading. This is individual trains passing, right? And as you can see, there is a big, there is this, the axes are the same. So look at here, it's, or the axis scale. So it's about 0.33, it's about 0.1617, about similar something, and then as you go down, it's much lower than that. That's obvious, right? As you go down, stress levels go down, so your deformations are going to go down and stuff. This is Acela Express. Basically, this is a type of train. It has 32 wheel axles, and this is, this is the beauty of instrumentation. You can actually take a look: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. That's 32 axles right there. You can count it. This is your load cell measurements, load measurements on the track as the wheels are going, right? And then you just, these are the track settlement trends. Why did that happen? This is GPR data. Does everybody know what GPR is, or anybody has heard of it? Ground penetrating radar. Okay, it's very commonly used to measure, in pavements like pavement thicknesses. These days they can actually measure pavement layer densities using that. There are methods as well. In roads, it's very commonly used to study the quality of the ballast layer. If it is fouled, not moisture, no moisture and stuff like that, right? So this actually is GPR records. This is what is known as running roughness measurements, and there is a way to read this. The y-axis or the vertical axis is time. Okay, think of it as an increasing time. So it's 60 months. So 5 years of data here. What this means is red means it's a very rough track. Blue is best track, green and yellow slowly getting bad to red. So imagine this. So it was red, 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 red. They came, fixed it. Then it became bad, 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 bad again. And then they came, fixed it. And then it became bad, 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 bad again and stuff. So this actually shows recurrent maintenance of the track. Okay. So we actually identified this location, and this is where we installed the sensors. And this, look, this is another location, but this is 60 feet. The previous one was 15 feet from the abutment. So very close to the abutment. So there is no compaction, there is no stabilization happening. It's very, there is some stress wave reflection happening and stuff. This is 60 feet. 60 feet is like what? 20 meters. It's far enough where they are not worried about resonance. They're stabilizing or whatever, however the material is. So look how less the permanent deformation is. It's not just stabilization, by the way. There is a lot of stress wave reflection happening, because when the trains are moving, the stress waves moving through the layers, right? They actually rebound from the abutment and they cause all sorts of havoc and stuff like that. That's basically that. Okay, then we did some remedial measures. We actually we went and fixed the ballast layer, and we again measured, right? Look here, so this is settlement of previously, and then we went and did some measurements, remedial measure. I'm skipping like crazy because I want to show no, I don't want that. I thought I had some. Okay, let's talk about this a little bit. This will be a good leeway to some discussions tomorrow and stuff. Now we are talking about support conditions. As what did I say? Pavements and railroads are very similar as long as you are eliminating the train or rail and the tie and stuff. Underneath the tie, it's pavements. Same stuff. So now you can monitor support condition underneath the tie, which is basically a substructure assessment. So this is load cells. We'll go into a lot details tomorrow, but what you can actually see is let's go. here. Let's go here. Take a look here. Wheel load 15 feet location. So the same train going, and we are measuring how much it is impacting the track. Okay, 15 feet location and 60 feet location away from the bridge, closer to the bridge. This is the equality line. Most of the points are here. What does that mean? What does this mean? This is an equality line, so it's on the bottom. So what does that mean? It's lower on the 60 foot, higher on this, right? Do you understand what I'm asking? X versus Y. If we have an equality line, if it's plotting below, X is greater than Y, right? That's what I'm saying. So what's happening here? On these tracks, on these locations, or because of this, on these dates, the 15 feet location has a higher wheel load than 60 feet. That's because there is a dent, there is an unsupported condition, it's banging it there. That's the problem. Something called missing ties and stuff. We'll get into a lot of this tomorrow. So then we use some GeoTrack, which is a modeling software, to model these. Again, mostly tomorrow, I think I will show this. This is, look, this is manual. There is no back calculation software for railroads. So this is back in 2013, 14 when I was doing this. This is the actual measurement. Then I just went and then just tried to do measured versus calculate. This is manual back, like you were doing yesterday. I was just manually changing values and stuff to match and then calculate. Yes. Very good question. There is actually, I think there is a number. I don't know that low. It's probably couple of 2-3 millimeters or something like that. I don't know. They don't really quantify it as a rutting. What they quantify it is called track irregularity and track surface profile differences, and there are specifications of that. But anything, even as epsilon value is bad, because you are talking about rail, steel on steel, right? So it's a very sensitive subject. So how much it degrades and stuff, and then you can actually back calculate the modulus values of the layers and stuff. Okay, one last thing I will show on this thing before we go into something else. This is some remedial measure we approached, and this is another thing called gluing of ballast we approached, and then we did something called under tie pads, and how that improved and stuff. I can show you this. So yeah, this is the team basically what we were doing over there. So I wanted to just give you a quick idea about how rutting or permanent deformation is important for railroads as well. One thing I skipped here, I just want to quickly say before we end up or before we stop or go into other things, is the same concept of constant confining pressure, variable confining pressure, like the moving wheel load, that becomes very significant in rutting. When you simulate moving wheel load, when you simulate rotation of stress paths, the material behaves very poorly in rutting. That's where you catch significantly. So even if in resilient modulus it's not simulated in a testing, it's very important to do it in permanent deformation. And this is some of the works that at University of Nottingham they did different PQ stress paths. This is A, this is B, C is this called constant one. C is basically what your standard testing applies, and D, E and stuff, you can actually change stress paths, and then you can have significantly higher permanent shear strengths and stuff. This is some P and Q for in actual airfield measurements. These anything below is extension states, anything above is compression states. Remember, in our traditional testing, we always stay in the compression zone. We never go into extension. But real data is showing that your actual material is exposed to a lot of extension because of the moving wheel load and stuff. So that's the reason it's very important to stay there. And these are like different stress paths. It's not possible to go over all of these. This is some test that was developed. We don't have time for all of this. Single path, multiple path. As you do a single stress path testing, your permanent strain is going to be, this is permanent vertical strain, this is deviatoric strain, and this is volumetric strain. You actually see changing. Both volumetric and deviatoric strains change when you study multiple stress paths. There are some test methods. We're not going to go into those details. Changing stress paths to study permanent deformation. Okay, that's pretty much it in terms of what I wanted to cover under repeated loading. So we still have about 14 minutes. So let me recap a few things. So most important behavior is repeated loading behavior for aggregates, unbound materials, right? Because they are loaded under repeated loading. Resilient modulus and permanent deformation. One is kind of an elastic response after some initial settlement. The other one is that settlement part, right? The resilient modulus is recoverable, so you can predict it from different properties. It is stress dependent, is material dependent, yes, and whatever. But the plastic deformation is not something that you should only look at elastic response to predict. You should look at strength to do that. So your strength of the material is very, very important when you look at permanent deformation. So when all of you running resilient modulus test, you can get by without running a shear strength test. But if you're doing any study on rutting, like you are doing study on shake, shear strength test is a must, because otherwise you have no idea what your stress states are with respect to the strength of the material. You have to quantify it as a percentage, saying that this is the percentage where I was and that is what it is. Because the first question anybody will ask when you're doing rutting study is, what's the strength? At what level of the strength are you loading it? Because that's very, very important. Then we talked about the models and stuff. Resilient modulus, we talked about different models, how to fit the model, what the models mean and what not. Why is that important? Is because that gives you an idea to take any stress state of predict a modulus for that material by using the model. Otherwise, you cannot just, no, you cannot have an idea about the modulus of a layer, because it's stress dependent. It's not a constant number, right? So then the question becomes, how would you take care of stress dependency in a layered elastic formulation or something? Just use sublayers. Just use sublayers, find representative modulus values or find representative stress, and then iterate on that. I think I told you this. So last thing I will say, we said this a little bit yesterday, but you are like, okay, how now I have sublayered, I have this layer, I'm going to sublayer this. Okay, and you are saying, okay, how am I going to now assign modulus values for all of them? Right? What I would say is assign, let's just say to start with, assign a value of say 30,000, right? And then apply a load, run your layered elastic analysis, learn your IIT PAVE or whatever you're trying to do. At this point, at this midpoint, find your sigma D, sigma C, or basically sigma 1, sigma 2, sigma 3 essentially. Sigma 1, sigma 2, sigma 3, find all three of them. right? Then using that, calculate theta. Then using k theta model, calculate MR. Then compare this MR to this 30,000 that you assumed. Are you close? If you are not, take an average of these two numbers, rerun the analysis. Take an average, let's just say this is 20,000. So the average of 20 and 30 is 25. So in your iteration number 2, make it 25,000. Run the whole analysis again. Then check. Once you are close enough, you're like, okay, this is my converged modulus. Now I am confident that for this layer, I can allow this, I can assign modulus and still be okay. I'm good, no problem. This you can do for thick layers. When you have 24 inches of aggregates, don't just assign one value, subdivide it, run some analysis and figure this out, how this is going to go. Which model is better? Is k theta model better, Uzan model better? Really no, pretty much anything will work. As you saw in your R squares, all of them gave very good R squares, I'm pretty sure, right? All the models will give pretty decent thing. Different purposes are more valuable when you are going to go do real extreme sensitivity analysis. But that's your way to iterate and stuff. Okay. For the tutorial today, what we are going to do is I'm going to start with showing some DCP data, some analysis of DCP data, how it is done and stuff. But I don't plan on spending more than say 20 minutes on that one. Okay. And then we'll go into I'll share IIIPave with you all, and then there is a small installation. You can install it, and we can actually look at IIIPave, what it does, what the software is, and you can have it. It's a research code. You can have it in your toolkit, and you can just run it anytime you want to do. It's a very, very quick run. You can have some ideas how the materials behave, what kind of things you can get, what is stress dependency, what is resilient modulus variation with the layer, and stuff like that, right? How many of you, again, masters and PhD students, or at least PhD students, I think I know the answer. How many of you have not been at all exposed to finite element modeling ever? Or you haven't even heard the name in a class or anything? Please be honest. 1, 2, 3, 4, 5, 6. Okay. All right. So let me teach you. This is my crash short course on what is finite element modeling. I have this way of teaching which I like. That's since I learned it. There is a circle. Okay. I want you to tell me the circumference of that circle. How will you do that? 2 pi r. That's okay. 2 pi r. You're not allowed to do 2 pi r. The only tool I give you is this marker. What do? You put it here, then you rotate it here, then you rotate it here. How many times? Maybe 8, 9 times. Multiply by the length of the marker. Good? What did you just do? You somehow discretize the circumference, but is it an accurate measurement? You missed all of these curves, right? Now I'm going to break this to 2. Because they're going to cut my mind. Yeah? But if I break this into 2, what will happen to your measurement? More accurate? Now I give you only the cap. More accurate, right? That's finite element modeling. You are discretizing a system into little elements. You are studying a very little element, You're trying to then assemble the entire thing together. That's what it is, right? Does that mean when I have a pavement for you or something, and now you're trying to and I have a crack over here or a slab over here, joint, and you're like, man, my layered elastic theory is not going to work because it's going to talk about semi-infinite elastic space and stuff like that. What am I going to do, right? You're like, okay, let's not worry about it. We're going to talk about very, 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 very small elements, and when we come here, we're going to change some properties here and whatnot to capture that. Other than that, everywhere else, it's going to be the same, and I'm going to assemble the entire system together, right? Then make an inference about this. So finite element modeling is a numerical method. It's not an analytic method. It's not 2 pi r. 2 pi r is analytical, right? PL cube over 48 EI is analytical. Have a solution to it. Numerical methods are you're discretizing it, you're studying something, you're trying to generalize it. So the best, an ideal condition, the best finite element method is what matches the analytical method for an ideal thing, right? For certain cases, analytical methods don't exist, right? He threw me this 2 pi r thing in a second. Now I'm going to do this and then give him this. Then his method is going to collapse. Then 2 pi r anymore, right? But your method is not going to collapse because your cap you can still measure. Right? So in pavements, now let's go. What do you talk? Layered elastic theory. There is a very common analysis thing called homogeneous isotropic semi-infinite elastic half space. Okay, what is elastic? You all know. What is semi-infinite? Half of infinite, right? What is half space? Half of a space. How does the space look? Probably a sphere or three-dimensional, right? Now you are cutting it. Why are you cutting it? Because you know where the surface of the pavement is. So everything below you is infinite. That's why the medium is called semi-infinite, elastic half space. Homogeneous, isotropic. All of these assumptions, if they hold, your layered elastic theory is good. If they don't hold, the layered elastic theory is going to break. Also, in layered elastic theory, every layer is modulus, one property, one Poisson's ratio, right? And everything is infinite in extent and stuff. You can't put a boundary. You can't say, I have a curb here, I have a gutter here, I have all of that, right? So if you can't do that in illipave, the illipave is still generalized, or not, sorry, it's a specific application. It still assumes a infinite extent in the horizontal. But what I'm trying to say is, if I give you something like an abacus or ANSYS or something, you can do anything and everything, right? You can model this chair, right? That's because it is being discretized into certain well-known shape forms like elements. There are beam elements, there are shell elements, there are octahedral elements. So for every element, you know the exact solution and stuff, and you're taking all of that, assembling that together, right? So that's what we're going to do at illipave. We're going to take a look at it, and you will see how it is different, and then we're going to play with that, and that should be our thing for today. Sounds good? We're done. 12:59. Okay, so if you have installed and if you have launched, this is what the window should look like. No, you're not able to install? Yeah, that's fine, just say yes. Right click. Yeah, more info or something, right click, it should do that. Baki kisi ka? Everybody? Good? Okay. So as I said, it is this is a research code that was written by Professor Thompson and his colleagues and stuff at Illinois. So ILI stands for Illinois, University of Illinois, and it is a axisymmetric finite element software. So again, you're only analyzing one side, the other side is symmetric, mirror image, right? So and it is 2D FEM. You're only talking about X and Z. There is no Y. There is no depth into that whatever. There is actually some superposition that's allowed, but it's actually 2D FEM. Okay. So if you look at it, these are the modules, wheel loads. You can select multiple wheels because when you're calculating the stresses, let's just say you're doing one wheel, you can do 3 or 4 wheels to do an axle or an aircraft gear completely, like if you have multiple gear wheels and stuff. So just do okay. Layer properties, how many layers you want to do. Let's just try something like 3, and you can play with it after I'm done. So this is layer 1 of 3 thicknesses. Again, I usually work in the US customary units. 4 inches, it's a bound material, and remember, as I said, for modulus you can remember the one number. It's 400,000 psi, which is a pretty representative asphalt modulus. It's 1. Again, asphalt here is elastic. Okay, viscoelasticity is not considered in ILIPAVE. There are advanced programs that can do this, not ILIPAVE. Okay, ILIPAVE was actually written more from a transportation geotechnics focus. It's not the focus is not on asphalt. Okay, it's a bound material, and then there are typical values as well. Poisson's ratio 0.35. You can just leave all of that assigned. Then go to number 2, layer 2 of 3. Now this is a granular material, and look, the moment you select granular, it actually gives you the select resilient modulus model, what kind of model you're going to use. Okay, K theta is the most commonly one used, but it also has Uzan and it has sigma 3, which is I think called the Bezos model or something, the one with sigma 3 only, not Uzan. You can actually select it to see the formation. See, it's K times sigma 3 raised to the power n instead of taking the entire thing. We don't use it. I usually use the K theta in here, and it has some values and stuff. And as I said, there are some default values, and the general rule of thumb is as K increases, N decreases, and K decreases, N increases. So if you don't know anything about a material, you don't know anything, a very good guess for a granular aggregate or crushed aggregate, 5,000 and 0.5. K is 5,000, N is 0.5, and this is in PSI. Everything will give in PSI, not KPA or MPa. Don't confuse that. And then there is a friction angle, Poisson's ratio and stuff. You can keep constant. 3 is subgrade cohesive soil, right? And what kind of model you have? Again, semi-log or log-log or the arithmetic, which is the bilinear. The bilinear is the more common one. Okay, take a look at this and tell me how you can simulate constant modulus. Like we are completely eliminating stress dependency of subgrade, and we want to cheat the system, cheat the program to still take K1, K2, K3, K4, but we are going to use only one constant modulus. How would you do that? Say again. K3 and K4, you can just set it to 0, right? The problem is if you set it to 0, it's going to give errors, right? You have to set it to really small values, but not 0. If you give it 0, it's going to, but let's leave it like that. Let's leave it for now, and we can play with it later. Then assign, done. Then FE mesh generation. So this is all about the mesh. You can actually, there is some automating meshing routines that are incorporated into this. There is user generated, and then read from existing input file. You can actually pre-generate meshes and define and stuff. You don't have to do anything, just leave it, just leave default. Okay, just click OK. Then execution details. So this actually talks about what are the run names and stuff. I'm just going to say GIAN course or 2024 GIAN. Okay, and then what are the, do you want to use more Coulomb failure criteria? Remember, this is what I said today. When you have more Coulomb, right, it actually does compare the stresses against the failure stresses at that element, at that location, and then it compares, and if it exceeds that, it actually redistributes, recalculates, making sure that that element is not functional and stuff, right? So you can just say yes, okay, because we have already input friction degrees, number of iterations, you don't have to change anything, just keep clicking yes. There is some threshold for convergence and everything, and that's pretty much it. Okay, and then you can just say file, I need to wow, something happened. It crashed on me. Did it crash on yours too? It should not. Let me check. 3, 4, 12. What's going on? Okay, let's do something, folks. Let's do an open existing input file, and if you go into the stuff that I shared with you, let me give you an input file. I don't know what's going on.
Okay, I need to figure out something. I don't know why it's crashing. I've tried this on this computer. I hope it's not. Did it crash for everybody or? Yeah, it is. Okay, give me 1 second. Give me 1 second. I'll get you some files. What? Open. Why is it doing that? I have no idea. Oh God. I don't understand why it's not running. I haven't run it on this computer, but you're saying everybody's is crashing, right? What? Oh, it's running. Okay. So it's probably my Mac. Uh, okay, good. So what we can do, should I just use your computer then? So WhatsApp download कर दो इन्होंने or I can use somebody. Tanmay, I can use yours. Do you have a HDMI port or something? Okay, good. That's okay, great. Thanks. Okay, I didn't realize it'll fail on parallels. Oh, you know what? Okay, now I know. Because this is the modern Mac with the Apple chip, not the Intel chips, and some of the codes written are actually based on Intel. So I'm pretty sure if you have a Mac with the Intel chips, it will work. It's okay. That's probably the reason. That's fine. I'm glad it's running. Okay. So you probably got it skipped a couple things. I don't know if you saw when you tried to run it, it gave an error and you had to select the program file. Is that what you had to do or no? Yeah. So once it runs, if you are not able to run, I can take a look. But here is what you can do. So this is the input exit file, and then if you look at it, it is now plotting the z displacements. Okay. So you can actually change it to normal stresses. Let's just do resilient modulus. Okay. And there is 360,000 to 400,000. So at the very top, the white points, this is where this top is the asphalt layer. So that is where the 400,000 modulus is. Just underneath, you have certain values, and then away from it, you have actually significantly decreased numbers and stuff, right? So that's basically showing the variation of resilient modulus in the layer. Okay. Now what you can do is you can actually say, you can do critical responses or even extract average modulus. So let's just say something like, if you can say enter the maximum radial extent used to determine the average element modulus per row. So we'll just do 0, which is 1:1. And what it is doing now, folks, is, because finite element, I mean, those of you who don't know, it's basically a grid, right? So you have the entire system is basically divided into grids. That's what the mesh is, and that is what in the mesh generation and stuff. So it's saying for this row, the average modulus is 400,000, which is asphalt. There is no change. Second is also asphalt. Third is also asphalt. Look at the thicknesses: 1, 1.5, 1.5. So they add up to what? 4 inches. That's what we defined on the asphalt layer, right? So that's the average modulus. Then you go down, row thickness is 2 inches and layer number is 2, and now the average modulus is 79,000. Then you go one more down, 60,000, 45, 36, 5,900, 6,000, 6,000, 7,000, 8,000 and stuff. Now how is it increasing a little bit? Why is it increasing a little bit? Look at the layer properties or layer number. Subgrade. Subgrade is stress softening. So when you have higher deviator stresses, the resilient modulus is low. When it is low deviator stresses and just under confinement, the resilient modulus is high. That is the reason you see kind of a reverse trend in there, right? And then you can also do critical pavement response. Like for example, you can just do critical pavement responses. What are you looking for? Search for bottom tension, yes. Search for top compression, yes. Search for top compression vertical strain, yes. So you're going to search. That now gives you the critical pavement response parameters: horizontal strain, critical stress at top of subgrade, and critical strain on top of subgrade. That's the epsilon V, that's the sigma V, both of them, right? Why is that important? Let us say that you're not doing MEPDG, you're doing some very basic stuff where you are saying NF, number of cycles to failure, is equal to some kind of K multiplied by epsilon T multiplied raised to the power some kind of K2. That's your pavement performance model for your agency, for your state. You go and say, hey, what is my resilient critical strain at the bottom of asphalt? Is 191.4 microstrains. So this epsilon T, 191.4 microstrains. You plug that in, you're able to put it into a model to determine the number of cycles to failure. Does that make sense? Do you want to start from scratch again so that we can go through the steps of running this, if those of you were not able to? Let's do that. Let's do that, because my Mac kind of threw me off. So let's close this completely. Start from scratch. Okay, this is IIIPave, right? So we're going to load. Here is what we're going to do. Let's do this. So one of you, maybe you tell me a table where you're able to run IIIPave. Anybody, any table you're able to run in the first run? You guys were able to run, all of you? No, just one. Okay, okay, you are able to run. So why don't you on your computer pull up yesterday's example, the layered elastic stuff we did in Python. Do you remember that? Tell me the properties. We're going to input the same property here. We're going to run that. Do you remember the link, the Google Colab? So let's go wheel load data. That's easy stuff. Wheel load data. Who remembers the radius? 4 inches. Remember that? It was yesterday 4 inches. So we're going to put in 4 inches. And what else did we know? We knew the load. How much was it? 9,000 pounds. Remember? I'm talking about yesterday's code, the Python code we ran. It was 9,000. Okay? That's okay. We're just doing one load. Now we go to layer properties. We started with 3 layers yesterday. So it was 3. Okay, layer 1 was thickness 6 and 18, right? I think it was. No, that is the 4 layer. 6, I think 6 and 18 was the first two. 6 and 18, right? Yeah. So it's 6 inches, and we said asphalt concrete. I think it was 500,000. Yeah. So it's 500,000, and it's a brown material. We're going to set everything okay. Click assign. Second is layer number is this is granular. We're going to do granular, 18 inches. Okay. Now this is interesting, folks. K theta raised to the power n, and we don't want it to be stress dependent, because yesterday's case was a constant modulus of 50,000. Remember that? So what we are going to do is I'm going to set this as 50,000. What should I do with n? If you do 0, it's going to crash. So maybe something like 0. I don't know if 0.01 works. Let's just stick with 0.1. It's going to probably be a little hardening, but that's okay. Maybe I should reduce it a little bit. Now 0.1 is a good number. Oh boy, sorry. So it's, let's just do 45,000. I'm going to do is 0.1. Friction angle, we're going to do a sign. Layer 3, look at the thickness. You can't change it, right, on layer 3, because the bottom layer in these things is semi-infinite always. In this case, for discretization, they have certain kind of depth already defined. And what was the value? 10,000. If you want to do 10,000, I would say let's set K2 to 10,000, and then we're going to do K3 and K4, both of them close to 0, right? Isn't that correct? Now we are setting the slopes to 0. Now it's almost a horizontal line. Are you catching what I'm doing? I'm cheating the system to make it horizontal, right? That's arithmetic. Everything else you can set, assign, done. FE mesh generation, you don't have to do anything. Execution details, you have to click through this. So you're just going to do test. Okay. And then save file. And we are going to do something like, we're going to call it test. Okay, save. When I do perform analysis, it's going to give you an error. That's just again, it's a research code. It was never debugged properly. So you just say yes. Now go to your program files wherever ELIPAVE is. In your C program files, whatever 86, wherever ELIPAVE is, you just need to select that. That's all. You open, and then it will now calculate, and as it converges, it's done. And then you just do test 2, and then save. So that's now your deflection, right? Oh, sorry, that's now your system. Let us do modulus first. So we are doing 500,000, and then okay, let's just do extract average modulus. Okay, look here. So the surface was 500,000, the bottom was what? The middle was 50,000. But look at the numbers. Because I had an exponent of 0.1, I didn't want it to crash. I could have tried with 0.01. Maybe it will work. You can try it on your own. I didn't want to crash it in the middle of the tutorial and then just lose time more. But the closer you stay to 50,000 or something, it's good. The bottom one, I think we did not do a good job. It's actually fixed at 1,000. We should have, maybe I typed 1,000 by mistake. Is that what I did? Let me see, where is test? Test, open, layer properties. Yeah, look here. See what I did? I missed a 0. 10,000. Assign. And then I think you will have to save file. Save. Yes. I think it will work now, perform analysis. Okay, good. Now we're going to do test 2. It's going to say save. Yes, that's it. Now we do extract modulus, extract average modulus. Okay, look, 500,000. Now look at the subgrade. It's 10,000. Do you see that? Okay. All right. So now I'm going to stop here. I'm going to go table to table. Let's just make sure everybody is able to run this, and then we'll talk about it more. Okay. Go ahead, folks. Try. Are you guys okay now? Is yours not running still? Try. But why not running?
It's not saving the files.
Oh, what kind of processor do you have?
Ryzen.
It's not a Intel, right?
No.
That's probably the reason. I'm assuming that's the. Is yours Intel? Yeah, that's.
At first it worked, but
No, it probably just now it's probably just an execution error. Just change your parameters. If it worked, it's probably the same. Did your works ever? No, right? It's probably what is yours? Intel?
Yes.
So why is that? Is you also getting some error or something, or what's going on? Still, yours also. What kind of processor is this? It is Intel 64-bit versus 32-bit. Is that the reason? Let me check Tanmai's. I haven't had these issues, folks. I have to run it on 64-bit. I'm pretty sure. No, he's also a 64-bit. Intel Core i5. I don't know about that. Yours running? Oh, it won't. What about yours? It's running? Okay, good. What about you folks? Yeah, oh God, we got. Yeah, go to this. Is it? What do you have? Is I can't see, it's too far for me. Displacement. Go to go to open existing input file. Did you save the input file? Check your inputs. Go to will load data.
The inputs are same.
Check again, just to be on the safe side. Go okay. Go to layer properties. 6-inch. Go to next layer. 18-inch theta model. this end, change this. I think we changed it to 0.1, right? Isn't, or did you 0.33? It's running. Figure out what's the difference. I'm sure it's running at least. Okay. No, so it output. No. I prefer this. Sit down. All files. So eta. So kota kochi. Is this the error per jota search korcho seta to? Just to go to all files. So select this one. This one, and then go open. No, what happened? Oh, got a second. Let's try this one because you have a space in there. I don't know if these things will work or not. I don't know. Again, it's save file. Let's just do that. Save. Yes. Perform analysis. Done. So now it's output files. You just do just whatever and then save. And then you just then you got reasonableness, extend reasonableness. Okay. हो गया आप लोगों को? हो गया? क्या चाहिए बताओ? तुम्हें क्या कर रहे हो? तुम तो गलत जगह पे हो ना? You have to go to your files ना? Program files. इली पे this one. Done. Yeah. आप लोगों का हुआ? अतः no? Yours will not work. You did your work? Okay. हो गया ना? Good.
What modulus representative will take?
That's the question. So you have to. So you can go to the middle of the layer, whatever is the middle. So how thick is it? It's 2, 2, 1. No. Thickness. You didn't do the 18. Do the 18 and then take the middle point or something. Yeah, that's fine. हुआ तुम लोगों का रन हुआ? Everybody? Okay. 1 second. I guess all 3. Okay, good. तुम लोगों का हुआ? पुष्पा खेला था मेरा? नहीं, yours run. So K does not matter because I will tell you. K2 is 10,000 because तुम देखो ना इसको तुम्हें straight line करना है. Just do mathematically. तुम cheat करो इसको. How are you going to make it straight line? K2 is this number, right? So let's just make everything straight around this. So K2 को 10,000 कर दो बस. तुम्हारा हुआ? Yeah, you have to do that. You have to click through that. हो गया दोनों? Okay. यार तुम लोगों का क्या हो रहा है? I have no idea. हो गया? Magic. तुम्हारा विश्वविद्यालय. Did it run? Okay. Okay. So this is a useful tool, folks, and then you can play with it to do whatever you want to do, right? So let's just do a quick thing. I don't have a lot of time, but let's just do a D0 query here and match with the layered elastic that we did yesterday. So do a query point. Who is with me? Can you do this with me? Query point. Okay, D0. Let's try 0, 0, 0. Deflection is about 19 mils. 19 mils is about, a mil is a thousandth of an inch. What is the number you have on the yesterday's? Huh? नहीं यार 16 था ना कुछ या कैसे 25 था क्या? How? Okay, okay. Now tell me what was the D0 from the Google Cloud yesterday, the collab. I can open it. हाँ बंद कर दिया भाई.